Yeah, I apologize for the delay. It matters to do this. Okay, so let us recall what we did last time. So last time we talked about conic varieties. So it is essentially a variety plus torus section. So we have some variety X, we have some algebraic torus. Active on it in such a way that that variety X itself kind of contains the whole algebraic torus as a proper subset, and the action on this algebraic torus inside of X is usual multiplicative action. So action of T on T. So T is the group, so we can turn this group operation as an action of torus on itself. So T1, T2 goes T1 times T2. Yeah, and action on X should be T. Yes. T includes X. So the action on X is like multiplication by T, and on a proper subset, this multiplication by T is like a multiplication in this algebraic torus. Okay, so that was kind of formal definition. And then we started kind of with some simple examples. Examples like, okay, we can take algebraic torus itself. So it is a Lie group, so it is a manifold, and it is a variety. So then we can take kind of C. So we looked at C, we looked at kind of some Cartesian products. So if we have if C is toric variety, then Cartesian products of two copies of C is also a toric variety with kind of toric, with diagonal toric action. So kind of one interesting example is one-dimensional projective space CP1, when we need to kind of look at the toric action in two separate charts and see that the toric action, which is multiplicative, agree with this kind of transition map that is also some kind of homogeneous transformation that goes to 1 over W. So then, from these simple examples, we went to kind of a construction for certain families of toric varieties. And in this construction was, so we discussed this as symplectic reduction. But there is a theorem that implies that if you perform a symplectic reduction of just kind of complex flat space like C, n plus s copies of complex numbers, molded by kind of U1 action that acts by some phases on these variables with some weights. And we perform this reduction at kind of regular value of a moment map. So we will get some variety x mu, which will be toric variety, and as long as mu is kind of nice interior point in the image of a moment map, so this variety would be independent on mu. So kind of this procedure of symplectic reduction is done in two steps. So on the first step, we kind of looking at kind of locus where moment map equals to mu, which we can denote as some kind of submanifold inside Cn plus s, which is G minus 1 of mu. So that is kind of pre-image under moment map of this moment map value mu. And then we motion by, so we look at, we kind of take an ordinary quotient by U1 action. So that naturally makes a dimension of this space x mu, like complex dimension, okay, real dimension of this space x mu will be what? Will be real dimension of Cn plus s. Dimension of x mu, real dimension is what? Is real dimension of Cn plus s, which is 2 times n plus s. And then first we take a kind of submanifold inside of this x mu, just treat it as a real submanifold, and this real submanifold is defined by some collection of equations, and for our kind of action by phase multiplication, so these equations would be algebraic equations. So we have like some collection of equations, and the number of equations is precisely kind of real dimension of the kind of dual algebra. So when we impose G of moment map equal to some particular value, so we are kind of imposing the number of constraints equal to dimension to a dual algebra, and in this case, Lie algebra for U1 to the power s is just R to the power s, and dual algebra is also R to the power s. So that's why here we subtract s. So that will be like s constraints imposed by fixing the level of the moment. And then we subtract another kind of dimension now of our group. So here, for regular value of a moment map, this action is free and proper. So that's why the manifold we will get will be a smooth manifold whose dimension will be precisely a difference of dimensions of J minus 1 of mu, and dimension of this Lie group and in this V group has also dimension S. So therefore, here what we get 2n plus s minus s twice. So we get here real dimension 2n. So far, like here, we constructed a real manifold, and okay, symplectic reduction implies that it's real symplectic manifold. However, there is some theorem that tells us that symplectic reduction with kind of our group, which is very simple abelian group. So that is result of the symplectic reduction is isomorphic to kind of what is called GIT quotient. And this GIT quotient is essentially we take the same space Cn plus S. So then we subtract some fixed orbits, like some subsets of smaller dimension, and quotient it by kind of complexified group. So here the complexification of this group U1 will be C star. So here we perform like just ordinary quotient, but quotient of Cn plus S with some stuff removed by a cis direction to the power S, and kind of obvious reasons the dimension of this space. So this space, because it's a complex quotient, will be complex space, and its complex dimension will be exactly n plus s minus s. So dimension will be s. And then the theorem basically tells that this GIT quotient is isomorphic to result of symplectic quotient. So I kind of prefer to talk about symplectic quotient rather than this GIT quotient, because in symplectic reduction, kind of sort of this procedure of removing extra stuff is sort of more straightforward and easier. So here, kind of this extra stuff is essentially what we like roughly remove by using the model. However, here today I will briefly tell you how to kind of explicitly get the stuff that we remove, like how to get some kind of equations for this subvariety that we remove from Cn plus S to precisely get x. But we are not going to use this GIT quotient in our course, and even this symplectic reduction, we will kind of use it very rarely, and our key, so that is kind of construction 1. So, but our key construction to kind of practically describe toric varieties would be construction 2 with this kind of toric varieties from polytopes. Okay, so let me kind of start with several examples before I will kind of phrase a formal definition of these toric varieties from polytopes. So let me start with C. So as we discussed before, so if you look at complex numbers with say coordinate z, so then kind of one-dimensional torus is just this star. So the torus action would take this point with coordinate z to z times t. So t is kind of non-zero complex number. Among points in C star, so we have two types of orbits for this point. So if v exactly to 0, so then kind of for all t in C star, so let's call it t upper script t. So it's kind of what happens to the coordinate after t action. So all kind of elements of C star, they preserve this point z equals 0. So and kind of 0 is orbit of G star, and furthermore, it is kind of zero-dimensional orbit. So while if I take a complex number which is non-zero, so then multiplication by t kind of in principle can turn any non-zero complex number into any other non-zero complex number. So here, like kind of for any w which is non-zero, there exists some kind of t such that w is g times t. So when you fix it, we can reach any non-zero point by literally just dividing one non-zero number into another non-zero number to get the key group element that we need to kind of reach that point. So therefore here kind of orbit is star, and this orbit is kind of one-dimensional orbit, and that is kind of C star itself, and then it is kind of proper subset here. And so therefore, we can describe structure of orbit on C. So C star orbit on C is kind of a union of two orbits. So it's kind of C star union point at zero. So therefore, our toric variety C is a union of two C-star orbits. Okay, and similarly, we can analyze other examples. So the kind of more interesting example is CP1, which I often would just call P1. So in this situation, kind of inside of P1, we have like affine chart C, and in this affine chart we also have. Okay, let me do it like this. So let me describe a point on P1 using homogeneous coordinates. So that are kind of parameterization for points on P1. So it's pair of complex numbers 0, 1, up to kind of overall multiplication by non-zero complex number. So now the action of C star in this homogeneous coordinates is kind of very simple. So it's yeah, okay, so it's, let's say it's like this. So T is not times Z1. So then for this action, if we look into a chart where the Z1 is non-zero, so there is such chart which is chart inside of P1. So in this chart we can use a kind of coordinate Z0 over Z1, and in this chart we have a point which is in homogeneous coordinates like 0, 0.Z1. So and in this chart that is the point inside P1, and this direction preserves this point, and that is kind of the same as the point in origin that we had in C. However, in CP1 we can look at another chart. U0 is a chart where Z0 is not. So in this chart we can use a kind of this idea that we can simultaneously rescale Z0 and Z1 by any non-zero complex number. So we can rewrite a kind of equivalent form of this direction, which is kind of better adapted to the other chart. So we just kind of rescale this pair of complex numbers by t minus 1, which is a non-zero number from C star. So that is our torus action. So then in this chart, we have another fixed point, which is z0.1 is also a fixed point of this direction. And then you can moreover prove that there are no other fixed points. So it means that for T1, and that all other points, like when we have, so all other points Z0, Z1, when both Z1 is 0 and Z0 is non-zero, so all these points, they actually, okay, all the points taken up to overall scaling is actually C star, which is one-dimensional orbit. Okay. So therefore, the structure of orbits on P1 has the following orbits. So we have like single one-dimensional orbit, which is this C star, which is isomorphic to this homogeneous points, where both Z1 is non-zero and Z0 is. So then we have two one-dimensional, like zero-dimensional orbit, which is, so it's the point at the origin. Let me kind of roughly call it z equals 0 in this coordinates. The number coordinate is 0 over z1. So this z equals 0 in homogeneous coordinates is essentially z0, 1, and z0 is not 0. So then, and there is yet another one-dimensional orbit, which is point at infinity. So to describe it, we actually need to go to a different chart when this point at infinity is defined. So, and not surprisingly, that it just kind of point at 0 when we switch to Z0 and Z1. So therefore, P1 is kind of a union of these three orbits of C star. And it turns out that it is kind of very convenient to depict the structure of these orbits using so we can depict orbit structure using certain polytopes. Let me kind of give you an example. So in a C star case, okay, so we have orbit which is C star. And for a C star orbit, we draw a kind of infinite line. So kind of C star orbit we depict on a polytope as kind of this non-compact real line. And essentially, kind of how to see C star, how to kind of C star from this picture. So these orbits encoding should be kind of one-to-one correspondence. So we should be able to recover, and to recover C star, we need to kind of fiber a circle on top of this real. So C star is kind of a circle, fiber it over R. So now, what if we have complex numbers? So for complex numbers, we have one orbit which is C star with this circle fiber over it. And then we add a kind of additional orbit. So that is kind of C star part. And then we add kind of at infinity of this real line, we add a point at infinity. And this point is just a point, so there is kind of nothing fibered or point fibered of it. And then to kind of restore our complex plane from this picture, so C star is kind of topologically a cylinder, so it's real line with a circle fiber top. So to get from a cylinder to a plane, we need to kind of gradually shrink the circle to produce something like a cup. So this kind of animation of zero-dimensional orbit, it kind of adds a cap to the cylinder to turn a capped cylinder into a plane. So similarly, in our example of CP1, so we have once again C-star orbit with circles fiber over it. And then we kind of add the two caps at infinity. Okay, let me start using this radial coordinates. So this real line or this polytope happens in some radial coordinates, and we kind of compactify this real lines, real line which is 0 to plus infinity, not including the points at infinity. So we kind of formally compactify this real line to infinite interval by adding 2 points at infinity, while to see back CP1, which is topologically a sphere, so we need to kind of add these points in such a way that the corresponding circle shrink to 0 radius, and we get like a slicing of some kind of squashed sphere, slice it into circles. Okay, so that was kind of a simple way of encoding, and this picture, when we ignore the circle part, so sort of kind of radial part of the picture, is what we call polytope. And it turns out that we can encode a huge family of toric varieties by kind of drawing certain polytopes and then assigning some kind of circle, or more general, if you have, say, two-dimensional, high-dimensional polytope, then we would have like a torus sitting over the middle point, and then as we approach various components of the boundary, so some of the circles on a torus would degenerate to a kind of lower dimensional tori, and we will kind of eventually get some. Okay, with compact polytope, we will get some nice compact tori. So now let me give you a formal definition of this toric variety from polytope. So definition. X is a compactification of C star to some power n by polytope P. Okay, and this polytope P itself is kind of okay. Let me give it like different. So is an intersection, like finite intersection. Let me call it HB alpha from 1. Let me call it capital B. So it's finite intersection with the half spaces. So we choose kind of on Rn. We choose a vector B, and then for a vector B, we can construct a kind of hyperplane for which this vector is normal. So HB is a hyperplane with, okay, it should be inward pointing. Okay, so here not what is inward pointing. Also, let's say the normal vector D. And then for this HB, we can define HB plus So that will be HB plus. So HB plus is half space. With okay, so for a kind of hyperplane, there are two half spaces. And to distinguish them, we should tell whether vector B is kind of inward pointing or outward pointing. So this vector B being inward. Okay, so we have this half spaces, and then in order to get polytope, we intersect this half space. Okay, so that would give us this kind of picture that it will be some n-dimensional polytope that we get by intersection of certain number of this half plane. So in particular, if there are no half planes, then we just have Rn, and Rn just represents C star to the power n, which is okay non-compact. Okay, let me add to be more careful partial compactification. So to allow a situation when I have like smaller number of hyperplanes such that this polytope is not compact. So that's why it's partial compactification of C star to the power n, and in particular, if there are no these hyperplanes, okay, no compactification, it's just C star to the power n. So now the more interesting part is what to do with angular part. So over each point, okay, let's say each interior point. So for this polytope, we have some boundary points and some interior points. So over each interior point, we have kind of, let me write it as 1 to the power n fibers. So here, over each point, we have kind of n-dimensional torus, n-dimensional real torus fitting over each point. So then, as we approach boundary, so for let's start with codimension 1 boundary. So codimension 1 boundary is kind of points lying on one of the hyperplanes. So codimension 1 boundary is kind of point on HP, or to be more precise, interior point on HP. So these HBs can intersect between themselves, so they would have like some boundary points. So let me just, like, if I have say 2 HBs, so let me take like a point somewhere here, which will be interior points on HB. And then for this interior point, for codimension 1 boundary point, we have S1 to the power n minus 1 fibers. But this S1 to the power n minus 1 is embedded into this high-dimensional torus by prescribing, or it is embedded by prescribing it's not anyway, so to specify kind of n minus 1 dimensional torus inside of n dimensional torus, so what we want to specify S1 minus 1 S. Okay, let me kind of write it temporarily like this. To specify n minus 1 dimensional torus inside of Dn, so is the same specifying kind of S1 that shrinks to a point. To a point as we approach the boundary point. So we kind of start at a point in a bulk, and we have n-dimensional torus sitting over this point, and then we gradually approach point on a boundary. So on top of point on a boundary, we should have n-1 dimensional torus, and therefore this torus should be somehow compatible with this approach, that we can still travel over smooth manifold, and this kind of specification, so F1 embedded into n-dimensional torus is characterized by its homology class. And homology class of F1 inside of n-dimensional torus is essentially a collection let's call them M of n integer numbers. All this mk they're integer numbers. So to specify a circle, we need to specify kind of windings of this circle over some basis in Tn. Okay, so therefore, kind of for each HD, we need to specify like some n-dimensional vector. Let's call it Mn. So n-dimensional vector, integer valued, okay, n-dimensional integer valued vector, and it turned out that to kind of make this picture smooth and make this kind of construction of various Tori fiber over various kind of boundary components. So to make everything smoothly glue into kind of complex toric variety, we need to make a choice that the vector B is proportional to vector M. And furthermore, the proportionality coefficient should be integer. So this B should be some integer number k. Okay, non-zero integer number k multiplied by. So therefore, in order to get a kind of smooth complex toric variety, we need to choose a very specific normal vectors in this radial compactification to polytope, and these normal vectors, they should be integer valued, and this kind of reason for being integer valued is because we also have like some circles and some tori fiber over different points, and we want these circles to kind of properly shrink to a point. So now we make an additional assumption. So that will be assumed for the rest of the course is that these vectors B are primitive. So primitive in the following sense that in kind of the collection of their components, B1 to Bn, is just a collection of integer numbers, and we want these integer numbers to have no common divisors. So we want the greatest common divisor for all these numbers, B1 to Bn, to be just 1. So that's kind of additional assumption that will be enough to kind of describe interesting toric varieties with interesting mirrors. However, maybe later it would be interesting to see what happens if we relax this assumption. So that would lead to to include some singular toric varieties, but for now let us kind of simplify our life by requiring that there is no common factor in this normal vector. Okay, so I think that finishes this definition. So once again, quickly recalling it. So X is kind of toric variety constructed from polytope P is kind of partial compactification of C star to the power n, such that we compactify radial part into some possibly infinite polytope given by intersection of hyperplanes. And the normal vector to these hyperplanes, they are integer valued vectors with kind of they're primitive integer valued vectors. And then to get a complex variety, we need to fiber a kind of tori of different dimensions, like over interior point of this polytope we fiber n-dimensional torus, and then as we go to codimension 1 boundary, we shrink one circle, and this circle with homotopy class defined by this primitive integer normal vector. And then if you go to the higher codimensional boundary points, say here, like going to this point, which is intersection of a pair of hyperplanes like HB1 and HB2. So for this point we have like on top of this point we have S1 to the power n-2 fiber, and kind of the choice of these two circles that shrink to 0 are circles with homology classes B1 and B2. And you can extend this procedure to kind of arbitrary higher codimension boundary points. So codimension K boundary point would lie on intersection of K hyperplanes, and these K hyperplanes would define exactly K circles with integer with kind of valid homology classes, because vectors are integer values, that will shrink to 0 on this codimension K boundary. Okay, so this construction is kind of okay. So the nice part about this construction is sort of easy to use, because what you do, you just pick up like some collection of integer vectors, like vectors B, and then just kind of intersect them, and the construction guarantees that you get some toric variety. So the disadvantage of this approach is that it's kind of hard to see what is the global structure of this thing, and it kind of generally it's sometimes tricky to recognize like some familiar toric variety on this picture. Okay. I think now maybe it's a good point to make a break, because the next thing which I'm going to talk is kind of how to go from this polytope picture to a symplectic reduction picture that we discussed last time. So in particular, we will see like how the polytopes emerge in symplectic reduction story, and how to relate, say, this collection. So here, the combinatorial data for our polytope, so kind of polytope essentially is just a collection, let me call upper, it's just a collection of some integer valued primitive vectors, while in kind of symplectic reduction construction, the combinatorial data for this variety was essentially a collection of weight vectors. So here, for U1 to the S action, we have exactly S weight vectors in n plus n dimensional space. So these weights are also integers. So therefore here we have n plus S times S dimensional matrix for these weights While here we have like, so all these vectors, they are in n-dimensional space, and we have a certain number b of this vector. So the data is n times capital B dimensional matrix with integer entries. And kind of natural question is kind of how to go from one combinatorial description to other combinatorial description. And that's what we're going to discuss after a short break. Let's make a 10-minute break. So, break. Before 11. I'll be back. Okay, so in the promise, we will now talk how to relate these two approaches, construction of toric varieties by symplectic reduction and construction of toric varieties by describing a top or describing toric varieties complexification of partial computation of C star to the power n by lower dimensional orbits. Yes.
How can we see that B should be proportional to N?
So that we see from kind of having here local structure of a manifold as some kind of cup in n-dimensional space. So as we approach the boundary, the circle should shrink to 0, and so okay. Let me even give a simple example. So kind of local complex coordinates would be something like r plus I phi. So if you have k coordinates like this, and then kind of going to approaching some boundary point means that we are going in some direction where r is kind of b times some large number. So we are going in a direction of vector b. So therefore, in order to kind of get the circle shrinking, so this kind of phi should be proportional to b over. Yeah, I think that's the best I can explain.
How can we identify this M vector as this M cycle as z to the power of M?
Yes.
Then what you want to show is this M is invariant at this hyperplane. The hyperplane is an orbit of this
No, hyperplane is orbit of C star to the power n, but it's lower dimensional orbit. So
it's invariant under this M action.
No, why it should be invariant? M is not defined in action. So M are not weights of some action.
M is correspond to the S1, this cycle.
Yes, but this is S1 that shrinks.
So it means S1 act trivially on, or S1 is.
S1 should act trivially, so that should be a fixed point for. Okay, yeah. So we can treat these M's as. Maybe as the weights of S1 action inside of a torus, and we want this S1 action to be trivial. Yes. So that would mean that one of the circles shrink. Okay, so like in kind of local coordinates and in examples, that's sort of straightforward to see.
It means this S1 act trivially on this hyperplane, or it's the hyperplane is invariant in the S1.
No, S1 should act trivially.
Surely.
So the hyperplane is invariant on the rest of the torus. So it should be n-1 dimensional orbit. So rest of the toric action should kind of move the points on the hyperplane around. So
the action is like the mk's power of this zk to the power of mk.
Yes, which is kind of equivalent to shifting r by b lambda. So if I have like action with these weights, so we have like zk and let's call it t naught parameter for this one, and kind of on a zk, the action is like zk multiplied by t naught to the power mk. So if we go to radial coordinates, so it will be like rk plus mk log t naught, log absolute value of t naught, and so let's say let's say that t naught is some radial part and angular part. So then it will be mk r naught. So that is shifting rk by mk. And here we have 5k and we shifting it by mk 5. Okay, so what we have? So for this, so this is hyperplanes, they're all at infinity. So here kind of the shift in the direction of mk sort of still preserves this hyperplane at infinity. But for faces,
you mean the hyperplane satisfy R? What's the definition of that hyperplane numerically?
So that was kind of R times equals lambda b, and we take this lambda b to infinity. So that kind of defined by hyperplane at infinity.
But why mk should be proportional to b?
Because I confused with the word shrink. I think it should be a quotient by a group, right? Quotient by a subgroup.
Okay, so shrink, shrink near the hyperplane, and okay, on the hyperplane, yeah, I think it should be. Yeah, it should be quotient by S1 action with some weights. Yeah, I think. Yeah, I agree. It should be quotient. Okay. Okay. I can't get like good explanation for why the weights should be proportional to vector B. So let me kind of keep it as my homework and return to it next time. Okay, so I will put the question here, and we will return to it next time.
So you mean the question is why these two quotient is same?
No. So here, like for torus part, we have a quotient, and for torus part, this weight should be integer. So that's the only way to kind of get a quotient to the torus of lower dimension, of one dimension lower. But then there should be an agreement between radial part and angular part. That it's kind of not two independent actions, but it was like a radial and angular part of a single C-star action. So in this C-star action, we kind of act on a radial coordinate by shift and act on a kind of angular coordinate by rotation. And the agreement of these two actions in the vicinity of hyperplane requires that this normal vector B is proportional to the vector M that defines a kind of circle over which we quotient n-dimensional torus. So and that was the question, like how to carefully see this condition from some local analysis near the hyperplane.
And for me, it seems that M and B should be perpendicular, because then it's like trivial, both in radial direction and angular direction.
No, it kind of no. M and B shouldn't be perpendicular because okay. So for radial action, so we have okay. So inside of C star to the power n, we have like our C star to the power n minus 1. And then this part of a C star should move points on a hyperplane around. So this thing should preserve hyperplane. So here kind of the non-compact part or radial part is r star to the power n minus 1. And in our coordinates, the action of this thing. So here we have like some lambda alpha. So they are just ways of this action. So the action is that r plus kind of lambda alpha. Okay, I need to separate weights and parameters. Let's say temporarily call parameters t alpha. So kind of for each element here is just some collection of weights lambda. So therefore here to preserve the hyperplane, so hyperplane is given by this equation equal to some infinite constant, but constant. So therefore to preserve this equation, we need to have a condition that kind of as we shift, this thing is 0. So this lambda b shouldn't change because lambda b is the position of this hyperplane. So that means that this lambda alpha, which are weights of a remaining C-star action, so they should be perpendicular to b. So the ones that kind of act on a hyperplane, so they are vectors perpendicular to b.
Why we consider the subgroup? We say the n-1 dimension torus as a subgroup of n-dimensional torus. But I think maybe we should think n minus 1 dimensional torus as a quotient of n dimensional torus. Because if we want to deform a fiber to a hyperplane, then we need to contract a torus. It's like we quotient a subgroup. So if we
Okay, but we can describe the subgroup as a kind of quotient group. So the subgroup generated by lambdas that are perpendicular to B, we can say that such lambdas, they are kind of general lambdas quotient by. Okay, so I wanted to quotient by lambda plus B, but that's not what. I want. Okay, so that is not quite the same. Yeah, so to construct a quotient, it seems that I need something like a unit, not unit, some vector with product with B being equal to 1. Okay, so let me not try to guess. Let me kind of talk about it next.
Okay, so this n minus 1 torus is it act on this boundary.
Yes.
Okay, so what was this S1 act on the total manifold, and
Yes. So C star to the power n acts on the whole manifold, but it has orbits of a different dimension. So
yeah. So can you explain again what is this S1 inside this t to the power of n?
So here we have like orbit whose dimension is lower by 1. So it means that some subgroup inside of a torus kind of acts trivial on it. So that the action is kind of not a proper action.
Okay.
So it means that there is some kind of stabilizer subgroup that acts trivial.
Yeah, this S1 act trivially, but there are other n minus 1
Yeah, and then they act like
yeah.
like freely. So
Freely, okay.
so they move the points around. And kind of to specify this as one, we need to specify like some collection of integer numbers. Okay, so yeah, let me kind of explain the relation to this other construction. So for symplectic quotient, we have this weight W1 to Ws, and the moment map. It is kind of has moment map with image in S-dimensional space, so kind of Lie group of this dual Lie algebra of U1 group is R to the power S. So therefore here what we would have the following thing. So these weight vectors, they have components. Let me call it capital A. So capital A runs from 1 to n plus s, so it's W capital A square. Sorry. dA absolute value square, and these weights, there are like s of them, and we will have a similar sums for all s weights. A from 1 to n plus f. So that is kind of a moment map that describes a map from C n plus s to a dual Lie algebra, which is R to the power s. Okay, and kind of to perform this quotient, we need to look at kind of G minus 1 of mu. So once again, let us describe mu in components. So mu1 to mu(s). So mu is kind of s-dimensional vector, and therefore this j minus 1 of mu is kind of a locus where we have the following S equation satisfied. So W1 A, sum of A, from 1 to n plus S, dA x square. Let me call it alpha. Alpha runs from 1 to S. Okay, so now let me introduce different coordinates. So let me introduce a coordinates rho A that will be real valued and will be absolute value square of Z. So this rho A, so they are valued in kind of R bigger or equal to 0, because the absolute value can take negative values. So let me describe this condition by saying that rho A are kind of real numbers, but with a condition that they are like real numbers bigger or equal to 0. And let me describe j minus 1 of mu in kind of this rho A coordinate. So then j minus 1 of mu is the following thing. So we have a collection of planes. So in rho A coordinates is just a collection of linear equations. 1 plus s equals a. So each of them defines a hyperplane in this R. Okay, so let me continue. So it's this condition, and then for all rho A's we ask it to be positive, and we consider rho A's to take real values. So that is kind of image of this j minus 1 of mu in this kind of radial coordinates. So in the radial coordinates, so first we take kind of a positive sector in this n-dimensional space given by this collection of inequalities that all rays are positive, and then we impose additionally S linear equations defined by weights of this U1 action. So therefore, this j minus 1 mu geometrically j minus 1 mu is an intersection. We impose this condition simultaneously of n plus s half planes. So these half planes, they are defined by this equation. Rho A are positive, so it's n plus s equations, and as hyperplanes that are given by this linear equation mu alpha. So something which is given by intersection of half planes and hyperplanes, so that is by construction a polytope. And kind of the statement is that this polytope let me call it P with subscript W. So it's polytope constructed from weights. So polytope from weights. From weights to detection. So then this polytope will be isomorphic to polytope constructed from this kind of hyperplanes, half spaces defined by collection of integer vectors. This, let me call it capital B. So capital B would be a set of this. Let me call it B, a set of integer vectors, and then polytope B subscript B. So that's the statement is that if we kind of construct this polytope from weights, then it will be the same as polytope for this vector B. So that kind of gives us a construction of kind of how to get a polytope picture from symplectic reduction. So let me give some examples, and then we will see how to get a kind of one collection of integer vectors, transfer one collection of integer vectors to another collection of integer vectors. Because for polytope, this relation is kind of easy, but for integer vectors, it is more complicated. So, but let me start with examples. So the simplest example would be to consider V1 as a symplectic quotient of V2 over diagonal U1 action. So we have like V1, V2 mapped into kind of rotation of V1 and rotation of V2 by the same phase. So it means that we have just one weight vector, which is two-dimensional vector. So this kind of vector WA and the vector. So it has the following components. So just 1 and 1. So W subscript 1 is 1 and W subscript 2 is 2. So now, because C2 is two-dimensional, so we will have two rows. So we have the following defining kind of equations for our polytope PW. So for PW, we need to impose that rho 1 and rho 2 are non-negative, and then we need to impose that rho 1 plus rho 2 equals to some mu. So that is WA, rho A in this case, so W1 and W2 are just 1. So that are kind of our defining equations for polytope, and let us just draw it okay, so let me draw this two-dimensional rho plane. So then, first we impose condition, so that will be like rho 1, and that will be rho 2. So first we impose these two conditions, that rho 1 and rho 2 is positive. So that gives us a restriction to kind of positive quadrant. And then we have this condition that rho 1 plus rho 2 equal to mu. And here we have several options. So let me start with mu positive. So if mu is positive, then this line defined by rho 1 plus rho 2 equals to mu intersects axis at the value mu. So that is this line rho 1 plus rho 2 equals to mu. And we are interested in this kind of simultaneous condition. So we are only interested in a part of this line which lies in the side of positive quadrant. So therefore, as a result, our polytope PW, basic polytope, is essentially a kind of an interval that is cut out from these equations, like two inequalities and one hyperplane equality. So then, if we change mu, say if mu is kind of exactly zero, so then as a solution we have just single point, and in the worst case scenario, when say mu is negative, so then let me say that here the mu is just that PW is just empty, so there are no common intersection points. So in this orange case, PW is just a single point, which is a point at the origin. And for positive mu, kind of PW is an interval. And indeed, if we analyze kind of moment map, we will see that the images of a moment map, which is absolute value of W1, absolute value of Z1 square plus absolute value of Z2 square. So the image of a moment map kind of only covers positive mu. So therefore, in kind of by taking a pre-image, we should take a pre-image of a valid value of a moment map. So mu better be non-negative. And then mu equals 0 is this kind of special points in these values of the moment map. So moment map take kind of image of the moment map is essentially semi-interval R plus, so it can take all values from 0 to any positive number, and this kind of point 0 is kind of boundary point of these values, and it is not a regular point on a moment map. So okay, so therefore, if you take symplectic reduction of a regular point, then we will get like this unique PW, which is interval, and this interval is kind of very same interval that we got when we described CP1 as a collection of orbits. So we have 0-dimensional orbits and 1-dimensional orbits. And we can kind of similarly analyze other type of symplectic reduction. So all we need to do, we need to kind of construct a polytope that is given by certain inequalities and some number of linear equations. So maybe one other quick example. So if you take a P2, it's kind of symplectic portion of C3 by U1 squared. So then, kind of what we will get a kind of three-dimensional roll space. So roll space would be three-dimensional, and kind of the positive. Now we need to take a positive octant. So it's kind of 1/8 of the space where all rolls are positive. Row 1, row 2, and row 3. Yeah. And then we need to impose one additional equation that row 1 plus row 2 plus row 3 equals some positive mu. And this equation will kind of cut out a triangle. So that will be like a plane that is cutting this angle, and the intersection of this hyperplane with this positive octant will be a certain triangle, and so in this case my W will be some triangle. And some kind of more careful analysis shows that this triangle is the same as this kind of polytope for P2, which is a standard triangle for P2. Is a standard triangle, so it is essentially a kind of polytope for C square, which is the semi-infinite polytope, which is just positive sector in a plane, and then we kind of compactify C square by adding another CP1. So in order to get CP1, we need to kind of compactify C square by CP1. So that means that we essentially added this additional CP1 here and completing this picture of semi-infinite polytope into a finite polytope in a sense of a standard two-dimensional simplex. So here PB two-dimensional simplex. Okay, so that's kind of a way how you go from one picture to another picture geometrically. So then to get a kind of algebraic relation between combinatorial data, you need to do the following thing. So first, like the polytopes that we will get by this construction, so this B is kind of a set consisting of some finite number of this integer valued vector. So the size of this exactly in n+s. So that's what we get if you kind of carefully analyze the properties of the intersection. So therefore we have kind of in PB description, we have a matrix that is n times n+s matrix, and in EW description, the weight matrix was a matrix which was like n times n+s times s. So that was kind of weight. So that was like s vectors in n+s dimensional space. And here we have kind of n+s vectors in n-dimensional space. So they are vectors E, alpha, and these are weights. Okay, that will go. Okay, let's call it BA W alpha. So then what we can do, we see that they kind of have, if we write this weight vectors and normal vectors into matrices, so then these two matrices will have kind of one common size, and having one common size means that we can multiply them. So let me specifically add indices. So W has like upper index A, which runs over n+s and the alpha. So similarly B. Okay, so the number of vectors is n+s, so I can label them with the same capital A, and they are vectors in n-dimensional space. So they are components. I can label with little a. So little a runs from 1 to n, capital A runs from 1 to n+s, and alpha runs from 1 to 12. So then the way to go from from kind of one data to another data. So given the W A alpha, we can do the following. So we can consider a kind of collection of equations. So we can look at this set of linear equations. So there will be like S equations, and then so it's S equations. And this S equations in n plus S dimensional space. So this, so that's equations in n plus S dimensional space. So given that the matrix is kind of full rank, that implies that we have kind of n solutions or n-dimensional solution space. So kind of all B's that are solved this equation. So all these vectors B understood as a vectors in n plus n S dimensional space. So all these vectors BA. So they belong to some n-dimensional space of solution. And then let us kind of choose integer basis in this n-dimensional space, and denote this integer basis v1 to the n. And that would be precisely our kind of normal vectors for a polytope. So normal vectors. So we got them by kind of looking at kind of integer basis for a solution to this S linear equations in S plus S dimensional space. So we get exactly n independent solutions, and then we kind of look at these solutions. Instead of n vectors in n plus S dimensional space, we can look at them as n plus S vectors in n dimension. Okay, so we essentially transpose this matrix to think of certain number of vectors in different. And then similarly, we can given these vectors B, we can once again also kind of consider this set of equations. So it's once again the equations will be in n plus S dimensional space, but now there will be n equations. N equations in n plus S dimensional space. And once again, given that we are dealing with a matrix of a full rank, that this matrix defined by B is a full rank, so generally it would mean that we have some S-dimensional linear space of solutions. And we choose some integer basis in this space, so this W A integer basis. And that would give us back kind of weights of the toric. So going into one direction, so for kind of polytope construction, so this kind of weights, they essentially define everything. So there is no kind of additional data. So given the weights, we kind of solve for these vectors, and given the vectors, we just draw a polytope by intersecting the corresponding kind of half spaces corresponding to this vector. However, if you want to go in opposite direction, so if you are given a kind of polytope which is intersection of half spaces for a given collection of primitive integer vectors B, so we get some weights W, but the weights W Okay. So weights W in the toric construction they also define everything. So the only kind of potential property is kind of to get GIT construction from these weights. But I think since we are not going to use GIT construction, so maybe I'll just skip that part for sake of saving time. So I will still add it to my lecture notes, and I will kind of send you updated lecture notes sometime later this week. So for kind of GIT quotient, so for GIT quotient we need to kind of subtract something from C n plus S to perform the quotient of the system to the and there is a certain also geometric construction of how to get this V of this extra variety that we need to subtract from n plus S before the quotient. So how to relate this V to these vectors B and how vectors B and then the polyton. How to get this V from just the polyton construction. But since we're not going to use GIT quotient anywhere in our course, so I will just leave it as some kind of home reading if you are interested. So for us, kind of prime thing is that in some applications we're going to need the symplectic quotient construction. So but for most of the applications we will just deal with this polyton construction for toric variety. So that's why all kind of you need to remember that essentially kind of this B and W they are like roughly orthogonal to each other. So they satisfy this kind of conditions. That properly packaged vectors B and properly packages weights W, they're kind of orthogonal to each other in n plus S dimensional space. Okay, so now let's see if we do this time. 45. Yeah, I think now it's actually a good time to make another short break, and after the break we will talk about one more thing. So remember when we started talking about Gromov-Witten invariance, which was kind of a side of a mirror, we mentioned that the Gromov-Witten invariance they're essentially like generalization of intersection theory on our variety. That's the simplest Gromov-Witten invariant, like degree 0, genus 0, was essentially just intersection of cycles on our X. So therefore, for these toric varieties, it would be interesting to see like how to get a certain handle on kind of cohomology groups, because that was our observables in Gromov-Witten theory. So how to describe cohomologies in terms of this combinatorial data, and then how to get like sort of product structure on cohomologies also in terms of combinatorial. So that would be our topic for after the break. And now it's 11:46, so let's make 9-minute break. Till 11:55, and then we will return and talk about cohomology in terms of combinatorial. I have a question for you. So have you seen my message like yesterday? So yes. So I talked to Andrei yesterday. So him and he said that because Louis is away today, so if you are interested, you can kind of talk to us in kind of usual time of Louis, which is like 2:30 today. But once again, if you are free at that time, so.
Yes, I'm free.
Okay, so then let us meet at 2:30 today, because for Wednesday Andrei doesn't know whether he give a talk or not. So let's kind of not rely on that and try to talk at 2:30. Okay, good. Okay, so let's proceed to a third part of our today's discussion of toric variety. So let me reset. So far we discussed two kind of constructions for toric varieties, and discussed how to relate combinatorial data, like weight vectors and some weight vectors of the one action for risk reduction and primitive integer vectors for polytope construction. And now, in preparation to Gromov fitting theory, on story X, so we look at the RAM cohomologies of X. Okay, so X are smooth, compact, so all the RAM cohomologies, they are kind of isomorphic to other type of cohomologies, so we just call them cohomology of X. And we will look at kind of triple intersections. So that is kind of simple as Gromov fit invariant. So if you have gamma A, gamma B, gamma C, so all these gammas, they kind of belong to some representatives of these cohomology classes. So we look at G naught 0 and kind of degree 0 Gromov fit invariant on X. So that is given by this very simple formula. So we just need to multiply this. I think I should probably just gamma 1, gamma 2, gamma 3. So we take a H product of this gamma 1, gamma 2, gamma 3 and integrate it over X. So that is, and if you know like a product on cohomology, so that is the same as a kind of standard pairing between gamma 1 and gamma 2 H gamma 3. So that are just some triple intersection on cohomologies, and that is kind of ring structure on this H star of X. So what we want to understand how to get question, how to compute H star of X and kind of triple intersection on it. Triple intersection. From combinatorial data. Of X. So first step is to get cohomologies. So for that we will use some nice construction. So for H star, we follow in the Fulton book on toric geometry, and he has like some very nice construction how to get a kind of H star of X. So H star of X as a vector space means that that we should get just some dimensions of these subspaces of cohomologies of different degrees. So essentially what we get from Fulton's construction, we will get what is called Betti numbers, which are dimensions of case cohomology Betti numbers. Kind of we can package these Betti numbers into what is called Poincare polynomial. So it's kind of Poincare polynomial for X. It's just a polynomial of a single variable that is constructed in a very simple way. So we take a summation from K to real dimension of X. And here we use Betti numbers as coefficients of this polynomial. So beta k multiplies e to the power k. So that is probably something familiar to you. So because we are dealing with a complex manifold, so if you have complex dimensions, so then it's summation from k to n. So now, kind of theorem that so for x given by a polytope, say polytope in this kind of with a collection of as I kind of claim it, these two polytopes are isomorphic. So given x constructed from a polytope and n is complex dimension of it. So then kind of Poincare polynomial px of t is given by the following formula. So the summation a goes from 0 okay. Sorry. This is some points. Okay, I think going from 0 to n, and here will be pk t squared minus 1 to the power k, and this pk is kind of number of faces codimension k faces no, sorry, not codimension k. I think it should be k dimensional faces. Faces of our polytope. So polytope P, it has faces of different dimensions, and here we also assume x compact. So x is kind of compact, constructed from a polytope, has complex dimension n, and then for this polytope P, we count the number of k-dimensional faces. We get this numbers pk. So then we substitute these numbers pk into this formula, and because here it's like t squared minus 1 to the power k, so we will get a kind of degree 2n polynomial. And because faces can go up to total dimension of p, so therefore this pk go from p0 to pn, and therefore the maximal degree of this polynomial is that k equals to n, so it's degree to n polynomial. And our Poincare polynomial, because x is to n has real dimension to n, it's also degree to n polynomial. So that is kind of very useful theorem. So it allows us to get from kind of counting faces of polytope to computing Poincare polynomial. So let me kind of just outline. So for details of the proof, I kind of refer you to Fulton's book, but let me just kind of outline or give you idea of the proof. Because it kind of uses some useful construction, which is I found interesting. Sometimes mathematics is about feeling and all things. So I kind of found this construction kind of rather nice and potentially useful for other application. So what Fulton did in his book, so he kind of started with kind of definition. So he defined it kind of virtual Poincare polynomial. And for virtual Poincare polynomial, so it has the following property. So he still calls it x of t, and if x is smooth and compact, so then this px of t equals to kind of usual Poincare polynomial. Yeah. Now. Okay. Let me call this with bar. So this virtual Poincare polynomial became real Poincare polynomial. So this idea of virtual Poincare polynomial is kind of extended Poincare polynomial away from this smooth and compact case, and to describe an extension. So he gave the following properties. So for other axes, f x defined by properties, and here he defined it in the following way. So if kind of y is closed algebraic subset of x, and u is just kind of x minus y. So then the x of t is the sum of y of t plus du of t. So if we cut kind of a subspace from x, so then kind of the polynomial, the virtual polynomial on x is just a sum of virtual polynomials for this kind of part that we cut it and the remainder. So then there are some other properties. I think not all of them are kind of independent. So some of them can be derived from other parts. So that's why kind of I will list them, because I will use some of them. So they are not all independent. So he has some lemma that kind of derives some of the properties from others, not all independent. So in the sense that you can define it given a smaller subset of properties, but I want to kind of define it with a bigger set to make my life easier. So so if my x is kind of union of finitely many closed subvarieties, so then the x of t is just sum. Well, I think this one is probably kind of can be proven from a first one. So for a third one, maybe it's still derivable from a first one, but just write it in the following way. So suppose I have my variety x, which is Cartesian product of some y times z. So for Poincare polynomial, like when you perform Cartesian product, Poincare polynomials multiply, and these virtual Poincare polynomials, they also have this this property that Poincare polynomial for Cartesian product is virtual Poincare polynomial for Cartesian product is a product of virtual polynomial. Okay.
Union means how to union it.
So I think it's disjoint union. Sorry.
You mean disjoint means this is isomorphism in this is isomorphism as a variety, or this is just stratification.
I think it's like union of orbits. So okay, so it's not quite disjoint union, but
so xk is like
so
locally closed subvariety.
yes. So it's okay. I'm not sure how to properly close subvarieties. in X. So
subword.
okay, sorry. There. Okay, let me say it this way. Like, so we are going to apply to toric X. So it's like union of C star to the power n orbits. So that's the only case which I need to apply. So in this sense, I think they are all kind of isomorphic to some C star to some power, and then kind of they gluing it over orbits of smaller codimension.
And they are disjoint.
Yeah, I think as orbits of different dimensions, they bound to be disjoint because kind of the say zero-dimensional orbit does not belong to one-dimensional orbit. So they are disjoint.
So you mean xk is a single orbit?
Yes. So xk is a kind of single orbit. So this kind of union will different orbits. Okay, so now what we can do to actually prove this theorem using this virtual Poincare polynomial. So theorem proof. So as kind of step one, okay. So our kind of key idea is to use like this property 2 and define a property. So for compact X, so Poincare polynomial of X by definition is this virtual Poincare polynomial. So now kind of X given from polytope means that X is kind of union of toric orbits Xk, and then we use property 2 to get here summation of these virtual Poincare polynomials for a different orbits. So different orbits. So all this kind of xk. So they are isomorphic to some star to some nk. So they are all orbits of a certain dimension, and furthermore we have this relation between kind of faces of a polytope and orbits of a different dimension. So for each k-dimensional face, we have exactly one k-dimensional orbit. So therefore, I can use kind of a structure of my polytope to rewrite it in the following way. So it will be a summation, and we will have orbits from dimension 0 to highest dimension n, because our toric variety always contains c star to the power n as its orbit. So, and here will be exactly number of orbits of dimension k, and here will be virtual polynomial for a k-dimensional orbit, and this k-dimensional orbit we can denote as c star to the power 2. So we are kind of getting close. So we are getting relation between Poincare polynomial and virtual Poincare polynomial for k-dimensional orbit. So now what we left to do is to compute this p of c star to the power k, and here once again I can use a property 3. So because it is Cartesian product of k orbits, so therefore here will be summation k equal to 0 to n pk, and here will be virtual Poincare polynomial for just one-dimensional orbit for a to the power k. Okay, so we are getting very close. So we reproduce it like some from k to 0, we reproduce number of k-dimensional orbits, and here we even reproduced some case power of k square minus 1. So what remains to prove is to compute virtual polynomials for T star, and for that we can kind of we can take some compact variety. So we know that virtual Poincare polynomial for compact variety matches with Poincare polynomial for compact variety. So let us take Poincare polynomial for CP1. So Poincare polynomial for CP1. So CP1 has only H0 and H2, and both of them are one-dimensional. 1 plus and kind of by this construction, we know that the CP1 has this kind of polytope for CP1, which consists of one-dimensional orbits and two zero-dimensional orbits. So that will be like T star of T that we are trying to find, and then we need to add a contribution from zero-dimensional orbit, but zero-dimensional orbit just points. So points, they are smooth, compact toric variety. So each point contributes to Poincare polynomial by just one. So for a point, you only have H0, so no others. So therefore, from this equality, we can solve for P of C star. So it's 1 plus T square minus 2. That is precisely T square minus 1. And now we kind of get a complete proof of the theorem that kind of dimensions of homologies packages in Poincare polynomial given by this simple formula. So let me kind of make two important remarks about this formula. So for remark 1, so by definition of Poincare polynomial, so in Poincare polynomial, so all coefficients are positive. Because all coefficients are dimensions of some vector space, so they are positive numbers. However, here, like if we raise T square minus 1 to the power k, we will get like some possibly negative contribution. But T square minus 1 to the power k has negative contributions. So in a sense that they give us kind of polynomial terms with a negative coefficient. So the kind of non-trivial thing is that the fact that these PKs, their number of faces for polytope, is kind of gives some additional constraint that removes all this negative contribution. That any time you kind of sum up these expressions, you will get a polynomial with positive contribution. So that's a kind of interesting remark 1. So just to kind of further illustrate remark 1, let me do one kind of computation. Let me do kind of examples to see how these negative coefficients cancel out. Okay, still better. So let me take X as a P2. So for P2, we kind of computed polytope today, and the polytope was so P2 was X for a standard simplex, standard two-dimensional simplex. So for standard two-dimensional simplex, so what kind of faces do we have? So we have kind of single two-dimensional face, so P2 is 1. So then for three-dimensional faces, for one-dimensional faces, we have we have 3 one-dimensional faces, and similarly for 0-dimensional faces, we also have 3 zero-dimensional faces. So let us use our formula to compute Poincare polynomial for P2. So here we take 3 zero-dimensional faces 3 times 1. So then we have 3 one-dimensional faces 3 times t squared minus 1. And then we have 1 two-dimensional face. So it's 1 times t squared minus 1 squared. So it is 3 plus 3t squared minus 3 plus t to the 4th minus 2t squared plus 1. So we see kind of bunch of potentially problematic negative terms, but all of them kind of get overrun by appearance of similar terms with a similar t degree from other contributions. So this 3 cancel out, and here this 3 cancel out with the 2t squared, and we got t to the 4th plus t squared plus 1, which is familiar Poincare polynomial for P2. So P2 has only one-dimensional cohomologies in even degrees. Okay, so that's kind of an example how this cancellation works. So let me make another remark too. Or maybe not a remark too, because it's not something that we ignore, but we're going to use it. So let me call it corollary. So that is corollary that we're going to use a lot in our tropical construction. It's also important for Gromov-Witten theory, because in the Gromov-Witten theory, we have a kind of very special role for two-dimensional homologies, because they define like this class of the curve, or they define the degree. So the dimension of H2 roughly defines like the dimension of this degree vector. So let us try to get a kind of beta 2 of x. So which is second Betti number. Second Betti. Okay. I want second. Second homology is paired with second cohomology. I think it's fine. Okay. So our space is a compact space. So it's dimension of H2. But because the space is a compact space, so Poincare duality basically tells that it's beta 2n minus 2 of x. And it turns out that it is easier to kind of track this thing, and this thing is kind of Poincare polynomial of x, and we are looking at a term as a coefficient in front of t to the power 2n minus 1. 2n minus 2. So that is kind of easier to track because in our sum, kind of the orbits of higher dimension, they come with a higher power of t. So that's why if you're interested in a power of t which is 2n minus 2, so then the only way to get to n minus 2 is to either have n-dimensional or n minus dimensional orbits. So Poincare polynomial of x 2n minus 2 come from two contributions. So we say that Pn t squared minus 1 to the power n, and here we are looking at the term 2n minus 2 of degree 2n minus 2, or it can be contribution from Pn minus 1 to t squared minus 1 to the power n minus 1, also t to n minus 2. So it's easy to get a degree to n minus 2 from this term. So from this term, the coefficient in front of 2n minus 2 is just p to n minus 1. So here we need to kind of apply some binomial formula and to get a coefficient to n minus 2. So it's actually minus n, because we raise 12th degree, times pn. So therefore what we get e n minus 1 minus n pn. Okay, and now, so what we know the following thing. So kind of by assumption, which I think I haven't phrased. So we always assume that the X is connected. So it means that it has only single orbit of the highest dimension. So it means that n is 1. So it's single orbit of C star, the complex dimension of X.
In definition of toric variety, this must be true.
Yeah, so we can, I think in the definition we assume that it contains C star to the power n as a proper subset. Yeah, so it kind of, secretly assumes that it is connected. Okay, so we don't even need additional assumptions connected, so we just call switch. Okay, good point. So that is from definition. And then what about Pn minus 1? So Pn minus 1 is number of n minus 1 dimensional faces. But this n minus 1 dimensional faces for polytope, which is intersection of half spaces. So the number of these spaces is precisely a kind of a number of these vectors p. So we denoted this capital B as the set of this primitive integer vector b1 to bb, and this kind of b is continuity of this set. So therefore we get this kind of nice formula that beta 2x is given by the following thing. So it is kind of number of these half spaces that we use to compactify minus complex dimension of X. So the second homology of X is kind of a difference between number of compactifying hyperplanes minus dimension of X. So in particular, I think if we look at another example, which is P2, or P1 cross P1. So P1 cross P1, we know that okay. So if you happens to do a homework or for some other reason, you know that P1 cross P1 has two-dimensional homology. So the degree of the map to P1 cross P1 is a pair of integer norms. So for P1 cross P1, the kind of the corresponding polytope is just a square, and this square drawn in two-dimensional space. So it has it is constructed as an intersection of four half spaces. So therefore this cardinality of B is 4, and kind of complex dimension of space is 2. So that gives a correct beta 2. And this formula we will meet it later when we will talk about tropical space. So now in remaining 1 minute, let me just kind of give you a kind of a formula which is a kind of very famous formula for this triple intersection. I will give kind of without derivation. We are both okay. So since I'm moving slowly than I anticipated, so most likely we are not going to get to defendant invariance. So that formula was kind of a preparation to kind of a preparation for some like Giventhal formulas for descendant invariance, and kind of since I'm not sure whether I will get to descendant invariance, so let me just give you this formula so you have an idea of kind of how to compute these triple intersections, but I'm not going to give details because I'm not going to use it. Okay, so so the key idea is existence of what is called Kirwan map. So which is mapped between cohomologies of symplectic reduction. So we have some kind of symplectic reduction of G action on M. So cohomologies of this space. So they are related to equivariant to G equivariant cohomologies on this M. That's like G equivariant cohomologies. On M. So given and this map is called okay K or kappa. Okay, so it's map K for K1, and then this kind of key result is that map K is surjective. So it means that given kind of form here, alpha in these cohomologies, so we can construct a kind of preimage K minus 1 of alpha. Preimage exists, but so for all alpha, preimage exists, but may be non-unique. So it means that we can kind of describe the cohomology of symplectic quotient as a certain kind of classes in equivariant cohomologies of M. And because our group G is just a abelian group, so equivariant cohomologies of M, they are very simple. So it's just cohomology of M with coefficients in kind of polynomial of S variables. I think I will call them phi1 to phi. And then, so that's kind of one key result. So that is another extra simplification property that for this U1 group, this equivariant cohomology, they have very simple description. And the third result is that using this map, we can map triple intersection, alpha 1, alpha 2, alpha 3, integrated over symplectic quotient G. So we can uplift this to primitives. And here perform some kind of equivariant integration over M. And it turns out that here, because this kind of equivariant cohomologies are kind of cohomologies with some polynomial with coefficients in polynomial ring. So for every kind of cohomology class alpha here, so we can for K minus 1 of alpha, so we can find a representative that is just kind of degree 0 form, so just a constant, but some polynomial of phi. So that is also always possible, and therefore here we can express this triple intersection understood as equivariant integration of M as some integration, as some residue integration for these three polynomials P1, P2, P3 constructed from kind of applying this inverse of Kirwan map. And this final formula and the integration goes over d phi 1 to d phi x. So, and this formula is kind of a generalization of our, yeah, I think I'm not sure whether I talked about like for P1 case, for Pn case, for x equals Pn. Okay, I think we talked that kind of cohomology ring is kind of isomorphic to this very simple ring that we take a polynomial of single variable and just mold it by a relation that phi n plus 1 equals to 0. Sorry, phi n plus 1 equals to 0. So that means that we have like classes 1 phi square and then phi to the power n and multiplication. This is multiplication with polynomial ring. So kind of when we talked about Jacobian rings, we said that kind of multiplication in a quotient in a ring that is some ring of holomorphic function quotient by some gradient ideal can be described in terms of residue formula. So we just P1, P2, and here we had like W prime, and we can pretend that that is our W prime because that is gradient ideal in one-dimensional case. So therefore, following our logic from Gromov-Witten theory, we can rewrite a kind of pairings in this ring in this form and kind of triple pairing. So if we kind of compose a pairing with multiplication in kind of polynomial ring, so we will get this kind of 3-point function or triple intersection or kind of structure constants with index raised by a metric from a pairing. So we get this kind of formula that sort of triple intersection in this cohomology ring is given by this residue formula where we take product of three polynomials, divide by phi n plus 1 and take a residue at 0. So that is kind of small contour around 0. Small s1 around 0. And this kind of application of Kirwan map and this.
Excuse me, what is the definition for this capital D?
Yeah, so that's where I'm going. So capital D is some polynomial and it's constructed in the following way. So if okay, let me so this capital D, which is denominator, is given by a following formula. So suppose my toric variety is given in terms of symplectic reduction with some double. So what I do, I take my weights. I think it has upper index A, so that is coordinate on which it acts, and has index alpha. So alpha labels different U1 subgroups. So for each U1 subgroup, we have own coordinate phi. So this alpha runs here. So alpha runs from 1 to n. So we kind of construct for each coordinate, we construct this linear combination of weight multiplied by corresponding equivariant parameter, and then we take a product over all kind of coordinates from 1 to n plus 1. Okay, and here I kind of missed a little bit. So here, in principle, I should write down some additional term that depends on this parameters mu alpha, because when we constructed toric variety by symplectic quotient, we need to take like j minus 1 of mu, and then this mu is kind of also enters this residue form. But I think for regular value mu, I think the answer is independent of mu alpha. So
this integral is what integral is equivariant?
So that is no. So this is equivalent integral, and that is all the ordinary kind of residue integral or residue at multi-dimensional residue at phi equals 0. Phi 1, phi 2, phi n equals 0.
So, sorry, this P is homology value.
No. So these P are just polynomials of phi. So first we say that equivariant cohomologies are cohomology of m valued in polynomials of phi. And then for equivariant cohomologies, you can always find like representative that is just pure
This
polynomial of
notation
phi.
means phi 1 and phi s, they belongs to H star n.
No. So that is extension. So it's kind of cohomology of m. So that are forms valued in polynomial ring. So it's a linear combination of differential forms.
Polynomial, their coefficients are in H star n.
Yes, but we can always kind of choose a representative in cohomology class whose coefficient is just constant in H star of m. So that is at least I think holds for this equivariant cohomologies with abelian group.
Because here you see this H star x itself is a
Yeah, it's as a ring. As a ring,
Yeah.
it's isomorphic to this one.
so it contains some torsion, something like. So this H star n here, if we understand it like this H star x.
Okay, so maybe here I should use different variable to avoid confusion. So
So when we do this like residue integration, this P1, P2, P3, they are omega.
they are polynomials of phi. So these p's are kind of polynomials of phi.
Yeah, but their coefficients are some polynomial of
So their coefficients are complex numbers.
no. But here H star x is not complex number.
Yeah, so that's why here it's omega. So here it's not phi. So once again, when you have equivariant parameters, you can assign to them some degrees, because your differential in kind of equivariant cohomologies. So it has the following structure. So it's Durand differential, and here it's equivariant parameter times substitution of a vector field that is generated by the symmetries. So here, this one, it has kind of cohomological degree +1. So it increases degree of form by 1. So that substitution of a vector field, it has cohomological degree -1. So it decreases degree of form by 1. So that's why the cohomological degree of phi need to be assigned by 2. So that's why here, if I have, say, polynomial which is phi 1 square, so in equivariant cohomology, so this would be equivalent to some form whose degree is 4. So this is kind of equivalent in equivariant cohomologies. So therefore, when I have just polynomial equivariant parameters, they still kind of carry information about the original degree of the form. So kind of degree of the polynomial in equivariant parameters is kind of a degree of the form.
Sorry. When I think only in this case when M is a affine space, the polynomial is not is a polynomial. In general, it's a cohomology value polynomial.
You say that I need additional property that the RAM cohomologies for complex space is kind of trivial.
Yes.
So okay. Sorry. Yeah, maybe you're right. That here our okay. That M is En plus S and kind of cohomology of M. So there is only H0 and that is okay. Yeah, I think maybe you're right. So
Yeah.
because I kind of used to think of of the fact that I can always find representatives, but that's probably intuition only from complex space, that I can always trade differential form into polynomials.
I'm still confused with if I know what is the polynomial P1, P2, and P3. This integral just the non-equivalent limit, just the constant term.
Yeah, so this is kind of equivariant integral, but this equivariant integral depends only on kind of cohomology classes here. And for cohomology classes, I can find like representative which is just kind of constant form times some power of phi. So kind of typical situation, like if I take, yeah, let me kind of give you an example, but that example would be on P1. Okay, so suppose I'm looking at equivariant P1, equivariant cohomologies of P1. So I have like Fubini-Study form that was kind of ordinary cohomology on P1. So then, if I solve this equation that d phi omega equal to 0, I basically see that Fubini-Study doesn't close under this equivariant differential. So because there will be non-trivial part phi iv omega Fubini-Study, and this one is non-zero. But it turns out that even though it is not zero, it is actually d of something. And kind of closed form would be okay, omega Fubini-Study plus phi divided by multiplied by some function.
Sir, this is not a simple case. The P1 is not a affine space, and the equivalent cohomology is not a polynomial over the cohomology of each sub.
Okay, yeah. That's a bad example. Yeah, so I need to take here maybe take C. So if I let's try to redo it with C. So on C I have like my U1 action. So my vector field is something like d over dt minus d bar d over dt bar. So now, so what I know that, so suppose I have some kind of two form on C. So then this two form, because this cohomology is, so that is C of phi. Yeah, so for any kind of two form, so this two form belongs to kind of differential form from C with say coefficients in phi. So kind of phi dependence is trivial, but then I can turn this two form into some polynomial that corresponds to phi. And the way to do this is that I just doing what? Yeah, let me kind of extend this form to a closed form under this equivariant differential. So the closed combination would be something like dv bar plus phi multiplied by some function, and this function would be something like.
I think it's very hard to consider equivalent Ram cohomology. Maybe we should consider equivalent singular cohomology in this case. Then the equivalent map just the quotient, the phi.
Yeah, but I think localization would work with any kind of cohomology.
Yeah.
So I think even though like here the function that we would get is kind of bad-looking function, like growing at infinity, like z squared. But in this equivariant integral, I can always add some kind of e to the equivariant differential of something without changing the integral. So I can add like some kind of term that will kind of cut out this growth at infinity. So I can probably produce something like z squared from applying this equivariant differential to something. So in kind of equivariant sense, I can still integrate functions that are growing to infinity. So I think I can probably still do it with de Rham cohomology, but it will be harder. So, but as I say, I'm kind of, since I'm not going to use this in a course, I just wanted to give you some kind of overview of how to turn combinatorial data, which are this WA alpha that we discussed extensively last time and this time. So how to turn them into some kind of enumerative data, which is like intersection numbers of some cycles. So intersection numbers is some enumerative invariant of X. And it turned out that to kind of turn this combinatorial data into enumerative invariant, you need to construct like a certain polynomial from it, and then kind of use a residue formula with this polynomial as denominator, and that would give you some interesting integer numbers that are kind of.
I'm confused with how this combinatorial data simplify this integral. I mean, if I know what is P1, P2, P3, I have know what is this integral should be.
No, but like suppose you have just random, not random, but I'm giving you like some collection of weights. So first you need to compute your toric variety to compute intersection. I'm not sure what do you mean by knowing P1, P2, P3.
I mean, oh, maybe the application is the alpha 1, alpha 2, and alpha 3 is given by some combinatorial data.
No, I think here we can choose P1, P2, P3 as kind of any polynomial. So I think there is a way to kind of describe. Oh, okay. I'm not sure whether I can describe a polynomial ring as certain quotient. Maybe. Okay, that's I'm not sure. But I thought that here I can use kind of any basis in this polynomial. So I can choose like P1 to be like phi 1, P2, phi 2, and so on. So that will give me a kind of intersection on some classes. I don't know like which classes, but what I want to have like multiplication structure on my cohomology ring. So yes, I don't know how these classes look geometrically, but I know that kind of cohomology ring would be sort of isomorphic to some polynomial ring with this kind of multiplication and pairing structure. I'm not sure like how explicit it is, but for some kind of Gromov-Fitts invariance with descendants, so we can kind of recover this formula as some special limit. So that was kind of my main reason for including it into course, because I planned to get to descendant invariance and to see these denominators appearing as from given Thales construction of some kind of 2-point functions or 2-point functions deformed by some observables. But now I'm not sure that I will reach there. So that's why let me leave it kind of sort of without good explanation and good proof. Just kind of as a piece of knowledge that I personally find useful, but I agree that it's not I didn't provide good arguments why it should be useful. So yeah, let me kind of treat this as very extensive remark that we can use this Kirwan map to compute some intersection of some classes which kind of not clear which classes. Okay, I think I'm already running like too much over time, so let's stop there. Okay. So,
Actually, in this last example, when you say M is C, then this MN singularity quotient you want becomes
no. So here it just was unrelated to singularity quotient. So we just were trying to illustrate like how to go from differential form to polynomial of 5.
Yeah, that's right. I see.
Yeah. So that's why I took simplest example.
Okay.
Okay. Yeah.
It's today. I saw it. Thank you for what please remind me because I think this is the usual.
Let's wait with two speakers. Investigate.
Do you have a for Christians? It should be about this.
You need that for every person.
I need that for just the announce.
You can find that see this website.
Yeah, it was similar to this.
You mean the poster?
Yeah.
Okay, I should check the OSS.
Yeah.
Because I downloaded
He also needs to
show.
this.
Oh.
那个太小了。我也是我昨天在大使馆干一些事情，然后我 appointment 是在11:30，我一直排到下午1点才到。
难点我可能还在想着，因为他这个reference 可以发给我在。好啊，
我在想，但是
呀，
我在整理，就是有些想法我还没有。
好，现场的操作。Okay, so let's begin. Okay, so last time we have proved the Cauchy identity. Just quickly recall the statement. Right, so as we have said, okay, so you look at this infinite product. Okay. Say so this is taken respect to two sets of variables, right? So you consider xi, yj just as two sets of formal variables, okay? So and then as we said, okay, so if you look at it, okay, so if you look at it just as a formal series, okay, right? So this expression is symmetric with respect to any permutations of the xi variables, and also symmetric with respect to permutations the yk variable. So therefore, it ought to be able to express in terms of the symmetric functions with respect to the xi variables and also the symmetric function with respect to yj variables. So the Cauchy identity is in particular this expression. Okay, also here lambda is a lambda runs over all partitions. Okay, and of course by S lambda x, we mean the Schur functions indexed by lambda respect to the x variables, and similarly for the S lambda y. So, and if you like, okay, so let's say if you like, you can write it in a more in a kind of graded form. So let's say you replace xi by I. T is just another formal variable, okay? T is just another formal variable. So then you get its identity. More in the form of the kind of generating function that we have seen before. Because S lambda, right? S lambda is a homogeneous polynomial. I'm sorry, it's a homogeneous function, right? Of degree equal to the number of blocks of lambda. So therefore, when you replace each variable xi by xi times t, so the effect is here. So t times the number of blocks of lambda. Okay. So, or if you like, you can also write in this form: sum over all n, and then sum over the partitions lambda with partition lambda n. Okay, and then s lambda x, s lambda y times t lambda. Okay. Now, there's a parallel identity, which is much easier. So as follows. So namely that instead of expressing the left hand side in terms of the Schur functions, so we express the left hand side in terms of the Newton power sum. Okay, right. Sorry, I missed out one factor. It's set lambda inverse. Okay. Okay, just quickly recall. So although we have already defined these terms, but just quickly recall. So so if lambda is a partition of n, okay, so then n factorial divided by z lambda, well, this number is equal to the number of elements in the conjugacy class of Sn with dipole structure given by lambda. Okay, right. So more explicitly, this number z lambda is defined by this. I to the mi times mi factorial. Okay, so where mi is the where for each I, so mi is the number of times, number of parts of lambda that is equal to I. Okay, yeah. Right, so it's a easy exercise to show that n factorial divided by this number is indeed this quantity. Okay, so this is a fairly natural quantity. Yeah. So yeah, okay. And we call that p lambda is simply by definition. So if lambda, the partition is lambda 1, 2, second, okay, say yeah, then p lambda by definition is p lambda 1 sum of p lambda m. Okay, when m is the length of the partition. Okay, so meaning that well, after lambda L, then the rest of the terms are just yeah. And of course, these are just the Newton power sums, right? So Tk, okay, so with respect to x variable is just well, essentially, so just the sum of the k power of each of the variables. Okay, right. Now, so we have seen that by the generation, the identity from the generating function. So this is what we have seen before. So ht, right? On the one hand, this is so let's say here let's say so just consider well okay so just okay never mind. So let's say here we just look at the case where you have the set of xi variables. So this is a generating function for the complete homogeneous symmetric function. Okay, but we have seen that this is equal to the exponential of the generating function for the Newton power sum. Okay, and the generating function for the Newton power sum is this one. Okay, and we have also seen that when you expand it out, this is exactly right, this quantity is exactly this thing, right? So sigma z lambda inverse, okay, p lambda times t to the number of box of lambda. So here again, lambda is over all partition. Yeah, so this is something we have seen before. So again, if you like, you can write it in this form: sum over n, and then sum over the partitions lambda, then a partition of n, and then z lambda inverse p lambda, and then t. Okay. Now, so how you get this? Okay. So the trick is as follows. Trick is consider of replacing the set of variables, right, xi by because after all, so the set of variables here just a countable set of if you like formal variables. So you can replace it or substitute by another set of countable. Countable set of formal variables. Okay, so we replace xi, so that by the set of product xi, yj. Okay. Right? Then, of course, then the left-hand side is exactly this thing. While the right-hand side, well, okay, right-hand side is exactly this, okay? It gives what we want. Because P lambda, well, okay, when I write P lambda, I mean this is with respect to the variable given by the products xi, yj is exactly P lambda respect to the x variable times P lambda respect to the y variable. Okay, so you see it easily, so suffice to check that for each integer k, that the Tk Newton power sum for k power respect to the set of mixed variables xi and yj is equal to the Newton power sum for the x variable times the Newton power sum for y variable. But this is clear, okay? So indeed, this is nothing other than a simple observation that this expression, right? If you look at this expression, this is of course just a product. I mean, of course, everything is just a formal power series. Okay, right? So which is this? So then, so therefore, when you make the substitution, this identity, okay, that we have already seen before, okay, then gives you this. Okay. Now, what is the point of these identities? So let me state it. Okay. So in fact, this is related to a certain natural scalar product that we can define on this on the algebra sim. Okay. So let me state it. Okay. Just yeah. Okay. So let me just state it because argument is just linear algebra, so let me not do it. Okay, if you like, I can go to McDonald's book. Okay, I give you the reference. Okay, so McDonald's book, chapter 1. Okay, so the argument is it's just linear algebra. So given these things, okay, given this identity, so the argument is just linear. Okay, so therefore, let me not do the argument. Okay, so we construct a inner product. Yeah, scalar product, inner product. Yeah, scalar inner product on our algebra sim by the following condition. That by the condition that the Schur function forms an orthonormal basis. So namely that the inner product of S lambda and S mu is equal to delta lambda mu. So namely that it is either 0 or 1. Okay, it is 1 only when lambda and mu are the same. Okay, so of course in particular, right, because the Schur functions are a set of we know that in any case it's a set of bases, and those lambdas that are partitions of n, in fact, is a basis, form a basis of the homogeneous degree n component of sim. So in particular, so that means that in this inner product, respect to inner product sim n are orthogonal, and it's not used. Yeah. Okay. All right. So of course you can certainly define this because as we have said the sure function form a set of bases. Okay. Yeah. So you can certainly define this inner product. Okay. But now so there's a characterization of this inner product in terms of the Cauchy identity. Okay. So and this is this argument from linear algebra. Let me erase this. Okay, so then this inner product and this inner product satisfies the following condition. Okay, so as follows. Okay, so for each integer non-negative n, if we have bases, we have two sets of bases, say u lambda and e lambda for string n. Okay, of course, these bases being indexed by conditions of n, then n and c below are equivalent. Okay, so A is the statement that the u lambda and the v views, well, it's basically they kind of due to each other, namely u lambda paired with v nu, respect to this inner product, this delta and u for all lambda u. Okay, of course, I mean D, yeah, okay, yeah, but I mean, yeah, maybe I should be more precise, okay, for all n and for all lambda and u that are participants of n. Okay, B is the Cauchy identity, okay, B is the statement that you have this Cauchy identity with respect to these u lambdas and the v lambdas. So namely, all right. Okay. So this inner product that we define by this condition, right? So satisfies this property. So namely that, or in some sense, is actually a characterization, characterizing this inner product in terms of this form of Cauchy identity. Okay. Yeah. All right. Okay. So that in particular, so we just draw the consequence. So namely that because you have of course, I mean in the case where you take u and v to be the Schur function, then it's just an original Cauchy identity. Okay, but because we also have this identity for Newton power sums, so therefore So applying this, right, to the case where the u lambda equal to p lambda, or more actually, but more precisely, because you remember in the identity for the Newton-Parson situation, there's this factor. Okay, so more precisely, so you normalize it. Okay, so then we obtain, right? So this obtained form. Okay, so respect to this inner product. Okay, yeah. So the inner product of this Newton-Parson p lambda p mu, this is equal to z lambda times lambda. Okay. Case. Okay. Okay. Right. All right. Okay. So now we come to the crucial part, and that is the relation. I mean, at this point, you already kind of can already guess that there must be some a kind of a deep relation between the Schur functions and the Newton-Parson. And indeed, it is. Okay, so that is in fact the most crucial part in the representation theory of finite symmetric. So of course, these things were first discovered by Frobenius. Okay, so now we now define the following Frobenius, of course. So the so-called characteristic. Okay, good. So for any this okay, so n, so here n, so n just fixed, and for any real value function on Sn. So here, so this is, if you like, just a group algebra of Sn, but you just for simplicity, we just restrict to the case real coefficient. If you like, okay, so this is just the yeah. If you like, you just set real value functions on Sn. Okay, right. So then we define define the characteristic map. Okay, so this is characteristic map. So character CH of N definition 1 over n factorial sum over elements sigma Sn of sigma, the value of n and sigma, times the Newton-Parson P evaluated at rho of, okay, so here rho of sigma is the well, it's the partition corresponding to the cycle structure of sigma. To the cycle. Okay, right? Yeah. So usual thing. So your element in Sn, right? So well, the conscious class of Sn is determine this the partition correspond to the how you're writing this as a product of disjoint cycles, right? So the partition is just of these links of the cycles, right? Arranged in a non-increasing order. Okay. So and in any case, so this element, right, this thing, this whole thing, right, is then in same n. Okay, right? Because this rho sigma, right, is itself. So this guy is then is a partition of n. So this rho sigma, then it does this is say partition of. Okay, right. And so therefore the Newton path sum respect to this rho sigma, okay, so like is lies in same n. Okay, right. So therefore this map, okay, this characteristic map is really sends the functions on Sn to same n. And okay. Now for us, we will actually only need the case of class functions. So in other words, functions f that are constant on conjugacy classes. Okay, so if f is a class function, so constant on conjugacy classes. Then, okay, so characteristic map of f. Well, okay, so then it's just right. So therefore, in this sum, you can just replace the sum instead of summing over elements Sn, you just sum over conjugacy class of Sn, which, as we have said, is parameterized by partitions correspond to the cycle structure of these conjugacy classes. So therefore, you can rewrite it in this form. Okay, with the obvious meaning. So this means, of course, the value of f at the conjugacy class, at the conjugacy class. Corresponding to rho. And here's the rho is just the is the conjugacy. Okay, yes, 0 is conjugacy. Corresponding to. All right. Okay, but you remember the formula that I have told you, right? This quantity, right, is nothing other than, so therefore this is, you can further rewrite it as sum over partition rho and of n, okay, z rho inverse, okay, and then f rho inverse. Yeah. All right, okay. Now, so we can now state the formula from Frobenius. Okay, so Frobenius formula. So for the partition lambda of n, we have the following. If you take the characteristics map of okay, recall that chi lambda, as I have told you okay before, chi lambda is what? Okay, so namely that this Frobenius give a parametrization of the set of irreducible representation of Sn in terms of partitions of lambda, right? Okay, so therefore chi lambda is the character of that irreducible representation parameterized by lambda. Okay, so of course, in any case, as I have said, okay, for symmetric groups, the values of characters are always real values. Okay, so yeah, so therefore it is in this setting. Okay, so the classic map of this is exactly okay. So if you like more explicitly, right? So just substituting f here as chi lambda, so you have the formula as lambda equal to sigma difference rows except row inverse chi lambda row. Right, so this is the Frobenius formula. Now, it should be said that in this formula, okay, so even though lambda and rho, I mean, even though lambda and rho are both partitions of n, right? But it is a kind of playing a dual role. So here, lambda parameterizes the characters or the irreducible characters or the irreducible representations of Sn, okay? While rho is the conjugate class. It parameterizes the conjugate class of Sn. Okay, so even though they are both partitions of n, they're same. They both partitions of n, but in this formula, right? They kind of like play the dual from the perspective group representation. Okay, so here, so rho correspond to conjugate class. Lambda correspond to the irreducible representations of or characters of this. Okay. All right. So this is Frobenius formula. Now, all right. So this actually is give the characterization of Frobenius parameterization of irreducible representation. So in a way, you can say that so in fact, so the parameterization of the irreducible representations of Fn in terms of partitions of n. Okay, you can say that it's constructed exactly so that this formula holds. Okay, it's constructed so that this formula holds. Okay, so in other words, so this formula, the Frobenius formula actually characterizes this parameterization. Okay. All right. Okay. Yeah. So indeed. Okay. So indeed. So that's easy to see from the expression for the characteristic map. In the case when f is a class function, right? So indeed, so that's easily seen. If both say f and g irreducible functions. On S and such that the characteristic map evaluated F and G are the same, then you see easily that F must be equal to G. Okay, this follows from the algebraic independence of the Newton parcel. You easily see it's just unraveling. Okay, so this follows. Just from the algebraic independence of the Newton parcel. The Newton parcel. Okay. So therefore, hence in particular, right, because characters are certainly their class functions. Okay. So therefore, if you can, that's the point. The Frobenius actually so he showed that for each partition lambda of n, you can exactly construct a character, an irreducible character, well, corresponding to an irreducible representative Sn, right? Whose character under this characteristic map is exactly S lambda. So in particular, indeed, this identity characterizes this irreducible character. Okay. Yeah. Okay. Okay. So of course we can also rewrite this in a equivalent form. Okay. So an equivalent form. Let me finish this, okay, and then the next lecture I will give a sketch, okay, for this. Okay. So equivalent form of Frobenius form. Okay, so of course as we have said, okay, Frobenius formula is this. Okay, set row inverse, which as I've said is really this quantity. Okay. Okay. Well, this is the Frobenius formula, but equivalent form. It's obtained by using a well-known orthogonality relation. Right, that is for any finite group. Right, for any finite group G. And time to get C classes. C1, C2. So if you look at this sum, okay, so the sum, this of course is complex conjugation, but in our case, okay, it does not, you do not need to concern it, because as I've said, for symmetric group, the characters are always real values. But in any case, so sum here, of course, sum over the irreducible representation of, well, I mean, G, okay, yeah, or equivalent, the irreducible characters, G, okay, yeah, so the sum on the left-hand side, right, so is 0, unless these two constancy classes are the same, okay, in which case the sum is this, okay, so 1 over the cardinality of the constancy class, okay, so therefore if you apply the orthogonal relation, okay, to this, then we obtain the following equivalent form of Frobenius formula. Yes. Okay, which is perhaps even easier to remember. Okay, so namely, so the equivalent form is follows. Namely, for any partition row, and then P row is equal to over partition lambda when time lambda divided row times. Right, so again, so as I've said, okay, so in this identity, rho and lambda kind of plays a dual role. So rho to be thought of as parameterizing constancy classes, while lambda to be thought of as parameterizing the irreducible characters. Okay, but kind of the, and of course you notice that this is exactly, I mean, these chi lambda rows, right, is form the change of coordinate basis, right? For between the Newton power sums P rows and the Schur functions length. Okay, right. Yeah. So and so, but this is the it shows the representations, or you also represent as symmetric groups. Okay, so is directly related to the theory of symmetric. Okay, so let's take a break first, and I give a sketch. Okay, this is not easy, of course, but at least I give a sketch how this is. Okay. maybe that's just okay. So before sketching the proof of this, okay, so actually, so as I've said, okay, implicit in this formula, in fact, is the Frobenius, the parametrization of the irreducible representations of Sn in terms of partition and n-thing, right? So in fact, so you can say that these two are done in the same package. So namely, we construct this classification of irreducible representation of Sn, right, in terms of partitions of n, and you show that this parameterization satisfies this identity, right? So basically, and I mean, it's done in a whole package. Okay, so yeah. So in particular, as I've said, okay, so this identity gives the, as I've said, the characterization of the character in terms of its visual functions. Okay. Okay. So, but before that, okay. So let us just also note one more example. So recall this characteristic map. Okay, as I said. Okay, so define. So right, one more time. So f is a okay, the new value. Okay, function. Okay, so namely just counter then the formula. Okay, just this. Okay, and this lies in same, okay, the degree n homogeneous component of the algebra of symmetric functions. Okay, yeah. So in particular, so let's say you take f to be, okay, so I'm using McDonald's notation. So yeah, so eta n, which is just the identity function on Sn. Okay, in other words, just take the value 1 on every element or on every conscious class. And of course, this is also equal to the character of the trivial one-dimensional representation. Right. Then the characteristic map evaluated in the well. Okay, so this term is just 1. Okay, so that is just this. That row inverse, row. Okay, now we have seen this before. This is exactly Hn. Okay, I mean the complete homogeneous symmetric function, right? Recall this is something we have just seen, right? It comes from this, right? So that this we have done number of times already, right? So this identity, right, comes from computing this, right? This identity between the genuine function for the complete homogeneous symmetric function and the genuine function for the Newton power sum, right? So we have seen that when you expand it out, exactly like this. Okay, right. So therefore, the classic map evaluated at that identity constant 1 is exactly the case. Okay. Yeah. Okay, before sketching the proof, so let me just make one more remark on integrality, even though this is not a crucial point, okay, but well, okay, certainly okay, good to mention this. Okay, now when we define this algebra of symmetric function, we allow any real number to be coefficient, right? So if you want to be more careful about integrality, so namely say if we define and lambda is the direct sum of this lambda. As in the way we define C and the C is just the direct sum of this C. Okay, except that we use Z coefficients. We use Z coefficients instead of real coefficients. So of course, if we use Z coefficient, then these are just Z modules instead of R vector spaces. Okay. Okay, so that then N is free set whose rank is equal to the dimension of the vector space sim N of rank equal to the dimension of the sim N. Okay, explain. Oh, this is just equal to the right the number of young okay of n boxes, or in other words, the number of partitions. Okay, right. Then we have the following. These symmetric functions that we have defined before, okay, they still form a basis as a Z module, okay, except for the Newton path. Okay, so let me just so all that things for lambda as a free Z module. Okay. Yeah. While for the Newton power sum, okay, so it is not basis as a Z module because indeed you might have denominator. So therefore, so at least if you allow denominators, so maybe these Newton passes indexed by partitions lambda, okay? Well, these is Q basis. Okay, so if you then scalar, you just form it as a product with Q. Okay, so which basically just means that instead of instead of Z coefficient, we use Q coefficient. Okay, then the Newton power sum is a basis. Okay, basically, I mean, this is something that you probably can guess, sorry, because of so ultimately it arises from these numbers, right? There's these things denominated. Okay, but in any case, and also the scalar product, the inner product. Okay, so the inner, remember we have defined this inner product, right, before on thing. When restricted to lambda, okay, so namely that, right, Z, right, if you like, it just means that the free Z module generated by the S lambdas, okay, the inner product on sim restricted to lambda is a Z. Okay. Okay. So now I can begin to sketch proof. Sketch proof of various form. And I again follow back down this book. Okay, so now I have to say that as you can imagine, right, because you're trying to classify the representations of symmetric groups, so not surprisingly, you have to use some techniques in ideas in representative theory. So if you're not that familiar with representative theory, so you just you can forget it, okay? But because we are not going to use it anymore. Okay? Next time we are going to begin to think about the probabilistic aspect. Okay, but yeah, but still the argument is certainly quite beautiful. Okay, so so for each non-negative integer, okay, so let us define. Okay, so maybe I should first say the following. Okay, so therefore, we construct the compensation of irreducible representations in terms of digits. Many small at the same time. At the same time. And then starting from next time, we just only use the Frobenius form. Okay, yeah. Okay, yeah. So as I said, okay, so we need to use some ideas in representative theory. Okay, so for each integer, so let us first define the following. So R n. Okay, of course, at this step we do not use the classification of irreducible representations, right? In terms of partition. Okay, that is still not known at this stage. So, but anyway, define Rn to be the free module generated by irreducible characters of Sn. Okay, so in other words, an element of Rn is a what? Okay, so it's a finite linear combination of the irreducible characters of Sn, and the coefficients are integers. Okay, can be both, can be positive, can be 0, and can be negative. Okay, so elements of Rn are usually called virtual characters. So these elements, elements of Rn called virtual characters. Okay, why is it called virtual? Well, this is simply because you allow the coefficient to be negative, right? So if you take a take a finite linear combination of the irreducible character and if all the coefficients are non-negative integers, right? Then this is the character of a representation of Sn, okay, right? But if some of the coefficients are negative, right, then it is not. Okay, so that's why in these elements are called virtual characters of Sn. Okay, yeah. So if you know something about Grothendieck group, okay, so then you can define it in terms of the Grothendieck of the category of representation of Sn, but I don't need that. Okay, so you just think of it, this is good enough. Okay, so an element of this is just as I've said, okay, you think of it just as a finite linear combination of the irreducible characters of N, and with the coefficient are just integers. Okay. Okay, so of course it's a just a free Z module. Okay, so Okay, so and yeah, so also yeah, so these are also the these are all also value functions. So in any case, these are real value functions. Okay, yeah, because as I said, the characters of Sn are in any case real value. Okay, yeah. And the rank of Rn, well, okay, so this is equal to number of distinct reduced characters. And right, so at this stage we are not assuming the parameterization, right, in terms of partition of n, but just by basic representative theory of functions, right? So the number of distinct irreducible characters of any group, okay, is equal to the number of colleges in class, right? So this is the number of distinct colleges in class. So therefore, indeed, so therefore this indeed, so this is the number of partitions of n, or the number of Young diagrams of n. Okay, yeah. So now remember, for each n, right, you have this thing, okay, and what we are going to do now is very specific to the situation that these symmetric groups can be embedded into a larger one. Okay, so in other words, we form to be the direct sum of these arrays. All right. Okay. So and we want to introduce we put a so the well okay, so in key construction. Okay, first is a again a inner product. And second, a ring structure. Ring, okay. Okay, so let us first describe the inner product. The inner product is easy. Okay, inner product is easy because after all these things, I mean, when you restrict to each, I mean, the degree n Rn, I mean, this Rn, and these are in any case functions on Sn, right? So therefore, you have the usual inner product on functions on Sn, right? So firstly, we have the usual product for functions. Yeah. So because we only need the real value function. So real value functions on and then so in particular for elements. Okay, so namely, so for say n and G in this right, so you show me the product. And because these are class functions, okay, real value, yeah, I mean, maybe I should, yeah, real value class functions. So maybe function, okay, right, so class functions. right? The usual inner product. So, and as I've seen, you can also write it in this form. Right, in terms of these numbers that we have introduced before. Okay. So and you just extend this inner product on the direct sum, okay, of these things just by taking by doing the obvious thing. Okay, so namely then extend it. So namely if n is equal to sum is g equals then the inner product g. Of course, I mean often find many terms at 0. So because these are lines. Okay, so they can just do it. All right. Okay. Now, so the ring structure is more subtle. Okay, but of course that's an important ring structure. It's actually a kind of graded ring structure. It's like this ring structure. I mean, the usual thing. As you can imagine, from the way you write this is actually a graded ring. Namely, this is a graded ring. Namely, that the product of an element in the degree n component times an element in degree n component is then to the component of the degree n plus n. Okay, so and so in fact, so this is of course a graded ring, and this ring is in fact okay, so which might be a bit surprising because groups are certainly non-abelian, right? But somehow this ring we are going to construct, okay, is actually complete. Okay, yeah. So now let me describe to you how this is done. Okay, so so to define the ring structure. So therefore, because as I've said, okay, this is going to be a graded ring, so it suffices to define. So suffice to define. Only need to tell you how to define the product between elements of or any okay. Now, of course, these elements, as I've said, right, they are so-called virtual characters, and in any case, these are class functions on symmetric group. Okay, so the construction is based on a general general construction in representativity known as induction or induced character. Okay, so firstly, a general construction. So for any finite group G, and in the subgroup H, say alpha being a class function H, let's define the induction or of alpha from H to G. Okay, so all right, so let us define or put induction of alpha from H to G to be the following class function G on G as follows. So namely, this guy evaluated an element G of the group G is given by this form. Okay, so now what this formula is, okay, so here sum over a set of representatives of these cosets of G respect to, cosets of H, okay, so the left cosets of H, I mean, of course, needless to say, so it's independent of the choice of the representatives, okay, so exactly because alpha is a class function on H, okay, so and here this expression is interpreted as 0. This is regarded as 0 if this quantity regarded as 0, if the quantity T inverse G times T, because alpha is originally it's a function on H, right? So therefore, yeah. So if this quantity, right, T inverse times G times T is not unique, you just interpret this quantity being, interpret this whole thing as being 0. Okay? So why is it called the induction? Well, it is because it's the situation in the case when your class function is the character of a representation of H. So if alpha is a character of a representation, which representation not necessarily introduced, then this guy, then this induction of alpha is the character of the induced representation of H to G. Okay. These you can find in any basic textbooks on representation functions. Okay. All right. So now back to our situation. Right to our case. So back to which we define as the sum of these. And just to recall, being the green set generated irreducible okay. So in particular, these are class functions on Sn. Okay, right, as we've said, a lot of times these are called virtual elements, and these elements are called virtual characters. Okay. Now, so the point, as I have kind of alluded to, is that so you can embed these symmetric groups into a larger symmetric. Okay, so the ring structure is then obtained as follows. All right. Okay. So now here, say we have an element Fn in the n greater p and Gm in the n greater p. Let's define the product. Okay, define this product by the following to be let me first write down and then explain. Okay, so here, so Fn cross Gm because it's regarded is well, okay, so in any case it's a yeah, just regarded as a yeah, is as a function as a function as a class function on the product as a cross. As in the obvious sense, okay? So in the obvious sense. Okay, right? Because Fn in any case is a class function on Sn. Gm is a class function on Sn. So we just regard this pair, right, as a class function on the product group in the obvious way. Okay? Right? So and in particular, right, you just we then apply this formalism with H being this product group, Sn cross Sm, and G being this larger symmetric group, S of m plus m. Okay, so and we invent the product Sn cross Sm, or in other words, we regard this as a subgroup of S of n plus m. And it's a subgroup of n plus m. By, well, of course, well, according to our convention, so S of n plus m is the symmetric group of the numbers 1, 2, up to n plus m. So therefore, for Sn, by let's say Sn acting on the number 1, 2, and n, while Sn acting on the numbers n plus 1, n plus 2, up to n plus n. Yeah. Okay. So therefore, by this way, we I mean, of course, in the obvious sense, right? So the way you, I mean, Sm is the symmetric group on the numbers 1, 2, up to m, but in the you let it act on the obvious way, right? On this set, okay. So and then so now, in fact, so you can simply you can we can invent Sn cross into x of m plus m by using any two complementary subsets. Cardinality and okay, without affecting the induced character. Okay, without affecting because the different way you choose these different complementary subsets of cardinality N and M are all conjugates. Okay, in S of M plus N. Okay, so. Because the different patterns okay. So therefore it does not affect, right? Because we don't remember, right? This thing, right, is a class function on the big group, right? So therefore, because the different way you embed this in this big group are all conjugate. So it does not really affect the result. Okay. All right. So now then can show this product structure is not okay if a commutative. This dot is commutative and associative. You can either check by direct computations, okay, or by using what I've said here, okay, yeah, what I've hinted here, okay. So, but in any case, and if as I've said, giving a structure, a gradient rate, giving this a gradient rate. Okay, now we are almost half of it. Okay, so key the form. I'm going to give you a sketch. Okay, you have to look at McDonald's book for the detail. Okay. But in any case, as I've said, okay, so we are able to do this thing only because of the very special situation that for symmetric groups, okay, you can embed it into a larger, okay, right? So if you're given any abstract group, okay, it's not a priori clear how one can do this thing, okay? But the symmetric group certainly very a special case. Okay, now key points first. So remember, I have defined this characteristic map before, right? So the first point is the following: the characteristic map. The characteristic map. Actually, so this defines an objective ring homomorphism from to 6 and preserves the inner product. On R. Okay, remember I have defined both before the inner product on sim, right? And also the inner product on R. Right? So, and the first point is that the characteristic map, right? So remember, as I've said, so the characteristic map sends, say, class functions in general, is saying any class function based on Sn to Sim n. Okay, so and of course, elements in Rn, the nth greater p's are in any case, in particular, well, these are virtual carriers on Sn, so in particular class function Sn, so therefore certainly you have it characteristic map sending these elements in Rn to Sim n. So hence, it gives a map from R to Sim. So the claim is that this characteristic map is actually a ring homomorphism. Okay, injective is something we have already seen. I have already told you before that when you restrict to the class function, the characteristic map is always injective. Injective is clear. So the key point is that it's a ring homomorphism respect to this ring structure that I told you, right? And on Sim, of course, the ring structure is obvious. I mean, just a product of these the usual ring products, okay, of symmetric functions, okay, yeah, and preserve the inner product. Okay. So this is a direct computation. So yeah, let me not show it, okay, because yeah, you need to argue something, but in any case, so let me just say that so for the ring homomorphism property, ultimately it is it comes from Frobenius reciprocity. But if you want to look at the details, just go to Thomas book. Okay. While for the inner product, for the preservation of the inner product, well, it comes from the identity that I have told you before. So namely that for the inner product thing, right? So the Newton function satisfies this. Okay. Right. This perhaps should not surprise you because right, in the definition, when you define this characteristic map for a class function, right? So f being a class function, and characteristic map of f is this. So which is a class function, say like this. So this Newton part shows up. Right? So therefore, when you want to check that this preserve or respect the inner product, right? So somehow something this comes up. Okay. So yeah. Now with this, okay, you will take this as granted. We can now almost finish. Okay. Okay. Oh no, sorry. That's the second point. The first point. Second point. Yeah. Just second point is this. Okay. Okay. No, yeah. Okay. Yeah. Actually, yeah. So so this is the first step. Okay. So and okay. So now with step one as granted. Okay, let's show the step two. Namely, the image of lambda is contained in the image of the characteristic map. Okay. Remember, lambda is basically same as sim, except that as I said, okay, you just replace all. You only use z coefficient instead of real coefficients. And of course, this is to be mirror with the definition of in the ring R and also these Rn, right? Because these are all just z modules. And so, and this step is the most, well, okay. As I've said, with one, we can now do this, okay? So suffice to show for each n and partition lambda each partition lambda of n that S lambda is in the image characteristics that is in the image of the characteristic. Okay, because you recall that lambda is the direct sum of the again the n greater p. Okay, with lambda and free Z module with these S lambdas, okay, being a set of bases, okay, as a Z module, free Z module. So therefore, to show this, suffice to show that each S lambda is the image of the characteristic map. Okay. Okay, I try to finish it quickly. All right. Okay. So let us put. So let us put I lambda to be the following. Okay. No, so first recall the notation. Recall the notation. So eta k is equal to the identity. I mean the constant function. Constant function. That's H, right? So any H or G. Constant function 1. So in particular, right? So you regard it as elements in right. After all, it indeed is the irreducible one-dimensional trivial representation. Okay. Then put the following. Then for each lambda, let us put 10 lambda to be this expression. Okay, as an element in infinite piece. Yeah. Now, what is this thing? Okay, so right. Okay, because you remember that I mean this as I've said. Okay, these etas are really the etas are these etas. Okay, and with the usual understanding that if the index lambda I minus I plus j is 0, I'm sorry, is negative, then you just interpret this entry as being 0. Okay, yeah. Now, so the determinant, after all, right? Yeah, if you expand the determinant, right, you just say multi-polynomial in terms of the entries. Right? So therefore, the way you compute the product is exactly respect to the product structure we have defined on the ring R. Okay, right? The way you interpret this, as I've said, okay, so instead of right, when you compute a determinant, instead of usual product of numbers, right, the product between the entries is by using the ring structure. I mean the product structure I have defined on R. Okay, right? Then you see that because right. So when you make the computation, then you land in the exactly the integrated piece. Okay. And furthermore, if we apply the characteristic map to this thing, okay, because characteristic map is A, then X the characteristic map is a ring homomorphism. That's why it's so crucial. Ring homomorphism. Right? When you apply characteristic map to kind like that, well, okay, so as I've said, right? So determinant is really just a multinomial, multi-polynomial of the entries. Okay, so therefore, when you apply the characteristic map and as given or granted that the characteristic map is a ring homomorphism, so you can put the characteristic map inside the entries. So this is equal to the determinant of characteristic map of eta lambda I minus I plus G. Okay, now remember I have recorded identity. Characteristic map evaluated as such thing, namely the identity function on the symmetric group, right? Sk is the complete homogeneous symmetric function at the index k. So therefore, this thing is equal to determinant of A lambda I minus I. Well, okay, this should remind you that this is the justification, the identity. Exactly. Okay, right. So therefore, this is now right almost we are almost there, right? So we have constructed a class function on Sn, right? Remember, so element in Rn is in any case is a class function on Sn, okay? Whose value under the characteristic map is exactly Sn, right? Okay, so it seems that we are almost there, but there's still one more thing to check. Okay, so in any case, this is already verified that each of these S lambda is in the image of characteristic map. But we are only trying to say that so this is, you can think of it as step 3. Step 3. So this I lambda that we have defined in this way, I lambda is indeed an irreducible character of Sn. Once we have shown this, then this completes the translocation given by Frobenius of the irreducible representations of Sn in terms of partitions, right? As I've said, because you show that this chi lambda under the characteristic map is S lambda, and as I've said, okay, if you know such a thing exists, okay, then it must be unique. It is uniquely characterized by this property. Then its image under the characteristic map is S lambda. So therefore, you only need to show that chi lambda is indeed an irreducible character of Sn, right? Not only as a virtual character. Okay, right. All right. Okay. So how do you do this? Okay. Now this is a general principle in representativity. I'm going to finish maybe in 5 minutes. Okay. By computing inner product. Okay. So indeed, you as the classic map serves inner product. Respectively. So let us compute the inner product. So lambda with itself. Okay, this is the inner product of Yeah, so given the granted the fact that it preserves the chaotic map preserves inner product. So this one is the inner product of sim. Alright, okay. So but we already know that the chaotic map of chi lambda is and as I have told you before, under the inner product on sim, well, basically is defined so that this inner system. Yeah. Now, so this we are almost there, right? So the chi lambda, remember chi lambda. Well, chi lambda in any case is an element in Rn. So therefore, in any case, chi lambda. Right? So if you like, okay, so it's a sum of the reducible characters, as in say a pi, a pi of integers. And remember, so that these irreducible characters are orthonormal, form a set of orthonormal bases with respect to the inner product you have defined. So the inner product of chi lambda itself is sum of a pi squared, right? Okay, so therefore, if this is one, that means that you can have only right exactly one non-zero term. Right? So therefore, which implies that chi lambda is equal to either plus or minus for exactly one. Okay, now we are almost there. We only need to exclude the minus case. So we do need to argue. I mean, it's not completely for free. Okay? Yeah, because the inner product computation only gives you this, okay, which is already a big step, right? So namely that in any case, right, you already know it must be associated to a irreducible representation of Sn. So we only want to complete the proof, just want to argue that you cannot have a minus sign. Okay, so in other words, this expression that we constructed is really the character of a irreducible representation of Sn. And so therefore, naturally, right, the lambda, the parameterization is given by associating lambda to this pi. Okay, right. So therefore, just to complete the proof, you want to rule out the case where you can have with the negative sign. So and this is the final step. Okay. So and then okay. So this so the final step just to rule out the negative sign. Okay. So final step. Okay, so now, so in any case, so and we already know that in any case, the characteristic map evaluated chi lambda is x lambda. Okay, so as seen before, using the orthogonality relation. Right, this is equivalent to the following. Okay, so for okay, so for any rho, so here of course I mean lambda is a partition of. Okay, so it's equivalent to the following. So for any partition rho of n, then P rho will be equal to sum. Lambda partition. Okay. so equivalent to this. Okay. In particular, let us evaluate this at the identity conjugacy class. Evaluate at the identity conjugacy class. Okay, so namely rho, right, correspond to the partition where all the coordinates are 1. Okay, yeah, so of course that n. Because for the identity, right, so you think of the identities, it is in terms of the cycle structure, just means that it's all the it's just a product of length 1 cycle. And each of these is just identity. Okay, so therefore, in terms of the partition structure, right, it is this. Okay, so then P, the Newton power sum for this partition, then is just P1. Okay, hence, gives. Okay, as I've said, taking rho to be the identity, P1 to the n equal to sum lambda for the partitions identity, okay, times this. All right, okay. Only need to show that each of these is non-negative, okay, in order to rule out the negative sign, right? So we only need to show. So we only need to show the coefficient. Yeah. So right. Okay. All the rule out that being minus, because as you know, right? If you are in this case, if you really have this case, then when you evaluate identity, right, this would be minus of the dimension of the representation, right? So there will be particularly negative integer. So in order to rule out this case, you only need to show that in this expression of writing P1 to the n as a linear combination of the S lambdas, okay, then all the coefficients are non-negative. Okay, so unfortunately, this can indeed be shown. Okay, this is using a special case, the so-called Peari identity. This special case is quite easy to prove. Okay, you can even try to prove it without looking at Macdonald, but in any case, sorry. But in general cases, it's more difficult. The special case is easy, quite easy to prove. It's as follows. So this special case of the Peari identity is the following. So for any partition, we have P1 times mu. Okay. Now P1 is homogeneous of degree 1, and S mu is of course is homogeneous of degree the number of box of mu. So therefore, the product is homogeneous of degree 1 plus the number of box of mu, right? So the Pierre identity is expressing this as a sum over the Schur functions lambda, and lambda, of course, is a number of box of lambda is exactly this. And in fact, the relation between mu and lambda is exactly this. Mainly, lambda is a Young diagram obtained by adding 1 box from mu. Okay, yeah. So this is a Pierre identity, general Pierre identity. And from this, one can prove easily like that. Okay. That when you like I give it to you, right? An induction of n on this n. Okay. That P1 to the n is equal to or sum of S lambdas with, of course, lambda partitions of n with non-negative coefficient. All coefficients in non-negative. And as I said, okay, so therefore this is enough to rule out this case. Okay, so and hence conclusion times lambda that we have defined is really time for a unique individual representation of okay, right, and of course this is so we associate okay, and of course and in the process of this proof we have already seen that the classic map take this to S length. Okay, so it's already this. Oh, so I'm sorry for running over, but I mean the argument is really beautiful, so I want to show you. I mean, maybe just remark. Okay, so although the presentation is modern, but I read from McDonald. Of course, I'm not able to read the original papers from Frobenius. Well, I cannot even find it. But according to McDonald, this is essentially the argument given by Frobenius himself. So, yeah. So although somehow you see the in some sense it is computational, okay, but it is a kind of it's something that you do not get in the general theory. Right? So of course we have a general representative theory for any finite group, okay, but the general theory is you cannot tell you this more specific information, right? For instance, for the symmetric. So and for the case symmetric group as we've seen, okay, so it's deeply related to the theory of symmetric functions. But in any case, so this is enough for our preparation. So next time, as I take it, okay. So next time, so we're going to look at the begin the Virchow Karov theory. So in other words, so namely that to classification of the characters of the infinite symmetry. The infinite symmetry. Okay? Yeah. Using what we have here, I mean this is the story for finite symmetric group, but taking these results as granted, okay, then we are going to look at how Virchow and Karov give the classification of characters at infinity. So in terms of, as we're going to, I'm going to state in the precise result, okay, the precise result next time. In terms of probability measures on the so-called Thomas symbols, this so-called comma simplex omega, which is a huge space. Okay, omega is an infinite dimensional, even though it's compact. Okay, but it's a compact metric space, but it's a huge, it's infinite dimensional space. So therefore, the situation is a bit once again a bit different from what one usually encounters, say in the representative of finite dimensional Lie group, for instance. So for finite dimensional Lie groups, or even in non-compact situation, right? So the irreducible representation are classified by, generally speaking, a finite dimensional space. Okay, so it's sometimes called you can say the support of the spectral decomposition. But for this, okay, so it's quite non-classical. So somehow the spectrum is given by this infinite dimensional space. Okay, and we are going to see, right? So then indeed, okay, some techniques or some basic techniques of probability theory allow us to so describe the situation. Okay, right. So let's and then we continue. Yeah, so next time we do not need to. You can forget everything. We are not going to use this. Okay. So this identity is important. We're going to use it in what follows. This is indeed. Okay. Yeah.
DGM 基本定位，全称中国网格集团有限公司，性质 啊，没事，你就
走了。
啊，没事，不影响你啊。
你们上课还上不上？
啊？
还上不上？我。
啊，不上，没事，你们忙就忙，没关系，不影响。
啊，好的。